The sleepy physicist is still here because some people refuse to let it disappear. If you want to keep it that way, the link is in the description.
There is something about the dark that makes certain ideas feel permanent. Not permanent the way stone is permanent, more like the way you assume, without ever deciding to, that the chair you always sit in will still be there tomorrow. You don't check, you don't question it. The assumption runs too deep for that. It's just part of the furniture of thinking. That's how it's been with black holes. The supermassive ones specifically. The kind sitting at the centre of almost every large galaxy we've ever looked at. For a long time, and really not so long ago, the working picture was simple. Galaxies spin, stars orbit, and at the middle of all that turning, the black hole sits, fixed, rooted, an anchor so massive that nothing in the galaxy could meaningfully nudge it. It seemed, honestly, like a reasonable thing to believe. The mass alone makes it feel intuitively correct. We're talking about objects that weigh millions, sometimes billions, of times more than our sun. Our sun, which already contains roughly 99.8% of all the mass in this solar system, and which you would have to place about 1 million Earths inside to fill. And then you multiply that by 1 million, or 1 billion, and the number becomes something the brain accepts without really grasping. The way you accept the depth of the ocean when you're standing on the shore. You believe it, but you can't feel it. So the assumption hardened. Quietly. The black hole stays. The galaxy wraps around it. This is just the shape of things. As many of you know, the sleepy physicist is supported by this community. Before that support started coming in, everything was on me, keeping this project running, making sure the people behind it could keep contributing, making sure it could keep going. Since you guys started showing up on Patreon, it has become a lot more manageable, and I am genuinely grateful for that. But I want to be honest, we are not at a comfortable place yet. We are a family of 25,000 people. Out of that, only 200 members on Patreon is all this project needs to run smoothly. Or just 30 of you in the co-creator tier is enough to make this place stable. That is how close we are. If this channel has ever brought you any kind of joy, or you simply enjoy what we make here, the Patreon link is in the description. What's strange is that nobody really argued for it. The assumption wasn't the conclusion of some major paper. There was no moment where astronomers sat down and decided. It simply accumulated, from the way gravity works at large scales, from the early observations showing black holes consistently at galactic centers, from the intuitive pull of the idea that the most massive thing in a system should also be the most still. A pendulum, if it's heavy enough, barely swings at all, right? Well, sort of, maybe. That's where it gets harder to hold, because the universe, and this is something that comes up again and again the longer you sit with it, the universe does not particularly care about intuitive pulls. It doesn't organize itself around what feels stable to us. It has its own arithmetic, and that arithmetic, once you actually do it, sometimes produces results that look nothing like the picture you had in your head. The black hole at the center of a galaxy is not sitting still. Not always, not necessarily. There are forces that can move it, slow forces, structural forces, forces that come from the deep architecture of the galaxy itself. And what those forces can do to something that massive over enough time is the thing this entire video is about. The assumption was reasonable. It was also, it turns out, incomplete. And somewhere in the dark outside this galaxy, a black hole is drifting. Start with something you already know. A star dies. If it was heavy enough, the collapse doesn't stop. It keeps going past neutron star, past anything with structure, until what's left is a point of density so extreme that the geometry of space around it simply closes. Light that gets too close doesn't escape. Not because it's captured exactly, but because the paths it would need to travel through in order to leave no longer points outward. Every direction past a certain threshold leads inward. That threshold has a name, the event horizon, and for a stellar black hole, the kind born from a single dying star, it might be a few kilometers across, small in the scheme of things, dense and violent, and strange, but physically modest. Supermassive black holes are not that. They are not a larger version of the same thing. the way a boulder is a larger version of a pebble. The difference is categorical. A stellar black hole might weigh 5 times what our sun weighs, or 20 times, or in the case of the heaviest ones caught in binary mergers, perhaps 90. A supermassive black hole weighs, and this is where the number stops feeling like a number, between 1 million and several tens of billions of solar masses. The black hole at the centre of our own galaxy, Sagittarius A star, sits at roughly 4 million solar masses. The one at the centre of Métis 7, the galaxy whose black hole we first imaged directly in 2019, is approximately 6.5 billion suns collected into one object, and the event horizon of M87's black hole is wider than our entire solar system. There's a pause that's supposed to happen here, and it does every time. The event horizon of the supermassive black hole is not necessarily a place of extreme local violence. This is the part that tends to stop people. The tidal forces at the edge, the point where you'd cross from the universe into whatever comes after, are actually relatively gentle for the most massive examples. Because the event horizon scales with mass, a sufficiently enormous black hole has an event horizon so wide that the difference in gravitational pull between your head and your feet at the moment of crossing would be barely noticeable. You would not feel it. You would simply be inside without the ceremony you might have expected. That detail feels almost rude somehow. All that mass, all that consequence, and the border is quiet. What makes supermassive black holes categorically different isn't just size, it's that they appear to have grown alongside their galaxies. Not after, not before, but in a kind of stubborn parallel development stretching back billions of years. The mass of the black hole correlates, with unsettling consistency, with the mass of the stellar bulge surrounding it. This is not a coincidence that astrophysics has fully explained. It is a clue, sitting in the data, that the black hole and the galaxy shaped each other, each one's growth somehow regulating the others, through mechanisms that are still in places genuinely murky. So what we're dealing with, before we start moving it, is this: an object of ungainly, almost obscene gravitational mass, formed in the deep past, embedded in the structural core of a galaxy, and connected to everything around it in ways that go far beyond simple gravity. It sits there, for now. What it takes to move something like that is a different kind of question entirely. A galaxy is not a spinning disk of stars. That image, the flat, elegant spiral arms curling outward like smoke caught mid-turn, is real. But it's the surface. What lies beneath it and around it and threading through every part of it is a structure far more knotted than the photographs suggest. Something with layers that don't announce themselves. Something with invisible mass doing most of the gravitational work, while the stars, bright and visible and easy to point to, account for only a fraction of what's actually there. Start with the halo. Not the inner part, not the disk or the bulge or the nucleus. Start with the outermost layer, the dark matter halo, because that's where the galaxy actually begins, if it can be said to begin anywhere. Dark matter doesn't emit light. It doesn't interact with anything electromagnetically. You can't see it, you can't touch it, it doesn't glow when it's disturbed, but it has mass. And mass curves space, and curved space tells everything else, gas, stars, black holes, how to move. The halo is roughly spherical. It extends well beyond the visible disk, sometimes many times further than the outermost stars. And it is heavy, in a way that the word heavy doesn't quite reach. A Milky Way-sized galaxy carries a dark matter halo of perhaps 1 trillion solar masses. The stars you can see, all of them combined, account for maybe 5% of that. I used to think of dark matter as background, passive. The stage everything else performs on isn't passive, not remotely. The halo's density profile, how concentrated the dark matter is toward the centre versus the edges, directly governs how efficiently massive object moving through it will lose energy and slow down. This matters enormously when galaxies merge, when black holes try to sink, when satellites fall inward and dissolve. The halo isn't watching, but it shapes the outcome of everything that happens inside it, through nothing more than the distribution of its mass. Inside the halo, the visible structure assembles, the stellar disk in spiral galaxies, thin, rotating, made of stars in organized orbits that have been stable in some cases for billions of years. And then, toward the center, the disk thickens into the bulge. More stars, more densely packed, moving in less organized paths, swarming, rather than orbiting in clean rings. The bulge is older, typically. It carries a different history than the disk does, and in the bulge's center, the black hole. Not sitting separately from all of this, not floating in a cleared chamber while everything orbits politely at a distance. The black hole is embedded, its gravitational reach extending outward through the bulge, touching the inner disk, pulling gas toward it from nearby clouds, occasionally triggering star formation, occasionally suppressing it. There's a gas component winding through all of this too. Cold molecular clouds in the disk, warmer diffuse gas in the halo, hot plasma extending even further out into the circumgalactic medium, that thin and poorly understood fog surrounding the galaxy proper. These components are not independent of each other. That's the thing. A shift in one changes the pressures on another. Gas flows feed the black hole. The black hole, when active, drives outflows that push gas back out. That gas, cooling and resettling, eventually feeds star formation. Those stars, when they die, return material to the interstellar medium, and the dark matter halo holds all of it together, or tries to, against the expansion of space pulling everything outward. Calling it an ecosystem feels almost too tidy. Ecosystems have rules that biologists can write down. This has rules too, but they operate across timescales of hundreds of millions of years, and they interact in ways that simulations are still working to capture. What's important for now is the texture of it, because when two of these systems meet, when two galaxies begin to overlap and pull at each other, everything in that texture responds. Nothing stays where it was. Not the gas, not the stars, not the black hole at the center. Nothing about it looks like a collision. That's the first thing. If you could somehow compress 2 billion years into a single minute and watch it play out, two galaxies approaching, overlapping, pulling at each other, eventually combining, it would look less like an impact and more like two slow exhalations mixing in cold air. Patient, structural, almost polite in the way that only things operating on incomprehensible timescales can seem polite. The stars themselves almost never hit each other. This is the part that tends to surprise people, and it surprised me too the first time I sat with it properly. Two galaxies, each containing hundreds of billions of stars, can pass directly through each other, and the probability of any two individual stars making physical contact is vanishingly small. Space is that empty. Even inside a galaxy, the stars are separated by distances so large that the galaxy is, in terms of actual matter density, closer to a very thin gas than to anything solid. What collides isn't the stars, it's the gravity. The approach begins long before any visible overlap. When two galaxies are still separated by millions of light years, their dark matter halos, those enormous, invisible, spherical structures extending far beyond the visible disk, begin to feel each other, not dramatically, a slow gravitational lean, each halo slightly distorting the motion of stars at its edges, tugging at the other's outer gas, beginning the long work of altering trajectories. This phase takes hundreds of millions of years, just the approach. Then comes the first pass. The two galaxies sweep through each other, and this is where the tidal forces do something genuinely strange and ungainly. As one galaxy moves through the gravitational field of the other, different parts of it experience different strengths of pull. The near side pulled harder than the far side. Stars on the leading edge drag differently than stars trailing behind. And the result of this differential pulling is that the galaxy stretches. Long streamers of stars and gas get drawn out from the main body, curling away into space in shapes that look almost biological. Thin filaments, loops, bridges of material connecting the two systems even as they continue moving apart. Astronomers call these tidal tails, They can extend for hundreds of thousands of light years. After the first pass, the two galaxies don't immediately merge. They separate again, still gravitationally bound but swinging out on a long arc, like, and I almost want to reach for the word boomerang here, though it's not quite right. It's more like two weights connected by a rubber band that's slowly shortening. They pull back toward each other. The second pass happens, then a third, each pass more disruptive than the last, each return bringing the centers closer together, each encounter stripping more material from the outer regions and scattering it into the space between. The gas responds most dramatically. Stars move on ballistic orbits, largely indifferent to each other's presence. But gas clouds collide. They compress. They shock heat. They fragment. Enormous waves of star formation can erupt in merging galaxies as gas is driven inward and compressed beyond the threshold where gravity overcomes pressure. Some of the most violently star-forming galaxies we've ever observed are galaxies in the process of merging, not because the merger is destructive exactly, but because it is compressive. It takes the gas somewhere it wouldn't have gone alone. The final coalescence, when it comes, is the quietest phase. The two nuclei spiral toward each other through a now shared gravitational potential, the remaining gas settling into new orbits, the stars gradually mixing and redistributing into the rounder, more diffuse shape characteristic of elliptical galaxies. The tidal tails slowly disperse or fall back in. The combined system breathes out into a new configuration. Somewhere in the middle of all of this, somewhere in the grinding, patient, billion-year process of two galaxies becoming one, the black holes at their centers are being carried along for the ride. Two black holes, each one embedded in what remains of a galactic core, each one now moving through a gravitational environment it didn't grow up in. What happens to them next is where things get genuinely complicated. Imagine moving through something that refuses to get out of the way. Not aggressively, not with any intention behind it, just present, dense enough that your passage through it leaves a mark, and that mark, that disturbance in the stuff around you, becomes the thing that slows you down. The resistance doesn't come from anything pushing back against you directly. It comes from what you leave behind. This is roughly the shape of dynamical friction, and it is one of the more patient, more stubborn forces in the universe, operating not through direct contact or electromagnetic repulsion, but through the accumulated gravitational consequence of motion itself. Subrahmanyan Chandrasekhar worked it out in 1943. The mathematics came first, as it often does in physics, clean, almost austere, in the way it reduced a deeply complicated gravitational problem to something tractable. And what the mathematics described was this. A massive object moving through a background of smaller particles doesn't simply pass through undisturbed. As it moves, its gravity reaches outward and pulls the surrounding particles slightly toward it. Particles behind the object get dragged a little closer to its path. Particles to the sides get deflected inward. The result is that the region of space directly behind the moving object becomes, over time, fractionally more dense than the region ahead of it. An overdense wake. Trailing behind like, and there's only one image that keeps coming back to me when I think about this. Like the way cold air thickens and settles in the low points of a room at night, not because anything pushed it there, but because the conditions created a preference, a slow accumulation that follows the same logic everywhere it operates. That overdense wake has mass, and mass has gravity, and the gravity of the wake pulls backward on the object that created it. The object is literally being dragged back by its own footprint. What makes this especially strange, and strange is maybe not the right word, but there's something almost philosophically uncomfortable about it, is that the drag doesn't require any physical contact. The particles in the wake don't touch the moving object. They don't brush against it. They don't need to. Gravity works at a distance, and at a distance is exactly where this braking force assembles itself, invisibly, through nothing more elaborate than the cumulative effect of many small gravitational nudges all pulling in roughly the same direction. The efficiency of this drag depends on a few things. The mass of the moving object matters enormously. Heavier objects create denser wakes and feel stronger pullback. The density of the surrounding medium matters too. A thick, rich background of stars and dark matter particles produces stronger dynamical friction than a thin, sparse one. And the velocity of the object matters in a way that is slightly counterintuitive. Slower objects actually experience stronger dynamical friction than faster ones, because slower motion gives the surrounding particles more time to respond, more time to accumulate behind the object before it moves on. Move slowly enough, and the universe grabs harder. This is the engine that draws two supermassive black holes toward each other in the aftermath of a galaxy merger. Each black hole, embedded in the remnant of its former galactic core, is moving through the combined gravitational medium of the newly merged system: stars, gas, dark matter, particles all swirling through the shared potential well. As each black hole moves, it generates a wake. The wake pulls it back, transferring energy from the black hole's orbital motion into the surrounding medium, fractionally heating it, fractionally accelerating it slowly, over tens or hundreds of millions of years, drawing the black hole's orbit inward. It is not fast. Nothing about this is fast, but it is persistent in a way that very few forces manage to be, and persistence across enough time can move almost anything. The two black holes spiral inward, closer, not because they're chasing each other, not because there's any direct attraction between them specifically, but because the medium they're both moving through is, at every moment, gently insisting that they slow down, lose altitude, descend. What's harder to hold on to is that this same mechanism, this patient, accumulated, wake-driven drag, is also the thing that eventually fails. That stops working. That leaves the two black holes stranded, close but not close enough, with no obvious way to close the remaining distance. But that comes later. For now, the drag is working, and the two black holes are falling toward each other through a medium that doesn't know it's helping. The dark matter halo is not decoration. It doesn't sit at the edges of the galaxy looking scenic, while the real physics happens closer to the center. It is, in a structural sense, the galaxy, the thing that organized the gas and stars in the first place, the gravitational scaffolding that held everything together long before the first star ignited. And when two galaxies begin to merge, the halos are the first things to interact, the first things to deform, and ultimately the first things to determine whether a displaced black hole sinks back to the center or gets left wandering. The key property is the density profile. Not the halo's total mass, though that matters too, but how that mass is distributed. How much dark matter is concentrated near the center versus spread out toward the edges. A halo with a dense, steep central concentration produces strong dynamical friction close to the nucleus. A halo with a shallower, more diffuse core produces weaker friction across a broader region. A black hole moving through each of these experiences a fundamentally different drag landscape. The same motion, but through a medium that either grabs hard or barely holds. In the standard cold dark matter model, halos tend to develop what's called a cusp, a steep rise in density toward the center, following a profile that climbs sharply as you move inward. In theory, this cusp should make dynamical friction efficient at small radii, should help pull in falling black holes toward the nucleus, and in some cases it does. But the actual situation in real galaxies is messier, because real galaxies have gas and stars and star formation and supernova feedback, all of which push back against the dark matter, flatten the cusp, redistribute the mass. The cusp becomes a core, shallower, wider, less grabby. Whether a particular galaxy has a cusp or a core, and how pronounced either is, quietly decides the fate of anything trying to sink through it. Now add the complication of a merger. When a smaller galaxy falls into a larger one, it doesn't arrive with just its stars and gas. It brings its own dark matter halo. and as the merger proceeds, tidal forces strip that satellite halo apart, pulling mass off the outside first, then progressively deeper, peeling the satellite down layer by layer as it orbits. The satellite's black hole, initially cushioned inside its own dense halo, gradually loses that cushion. The surrounding dark matter that was providing the drag, maintaining the friction, keeping the inspiral efficient, it gets stripped away. What's left is the black hole, still moving but now travelling through someone else's halo. A halo it didn't grow up in, with a density profile that may be far less accommodating, with far fewer particles close enough to generate a meaningful wake. This is where things can stall. Think of it, and this is the only image that feels right to me, like trying to slow down in water that's getting thinner around you. At first there's resistance everywhere, enough to steadily bleed off speed. Then the water starts to thin. The resistance doesn't disappear, but it weakens. And if it weakens faster than you slow down, you carry too much residual velocity into regions where the drag can no longer match it. You overshoot. You don't reach the center. You orbit, wide and lonely, in a medium that can no longer do the job it was doing before. The halo's structure is, in this sense, quietly decisive, not loud about it, not the kind of thing you'd notice by looking at the galaxy from the outside, but underneath the visible light, in the distribution of invisible mass, the question of whether a black hole sinks or wanders is already being answered. It's being answered slowly. It's being answered without announcement. But the answer, once set, tends to hold. There is a particular kind of vulnerability that comes from losing what surrounded you, not the loss itself, the after. The moment when the thing that defined your context, your weight in the world, your gravitational presence among other things, has been taken away layer by layer, and what remains is just you, smaller than you seemed, less able to move through the world the way you once could. This is, with uncomfortable precision, what happens to the smaller black hole in a minor merger. Minor mergers are the common ones, not the grand, roughly equal collisions between two large galaxies. Those are rarer, slower to assemble, more cinematic in their eventual outcome. Minor mergers are the ordinary business of galactic growth, a large galaxy absorbing a much smaller satellite, a dwarf galaxy, or a low-mass companion that wanders too close and finds itself caught in a gravitational relationship it cannot leave. The mass ratio might be 10-1, sometimes higher. The large galaxy barely notices in structural terms. The small one does not survive as a distinct object. And the small one's black hole, which had been sitting at the center of that dwarf galaxy, properly embedded, surrounded by its own stellar bulge and dark matter halo, held in place by the density of the material around it, that black hole begins a journey it may never complete. The stripping starts at the outside. Tidal forces from the larger galaxy reach into the satellite and pull the loosely bound outer material away first, the extended dark matter halo, then the outer stars, then progressively the inner structure, working inward like fingers peeling something apart one layer at a time. The process takes hundreds of millions of years and is, in its way, thorough. By the time the satellite's core has been significantly disrupted, the black hole that was at its center is no longer cushioned by much of anything. The halo that was generating the dynamical friction keeping it on course is threadbare. The stellar envelope that gave it gravitational weight in its local environment is largely gone. What's left is the black hole itself, bare, a point mass, enormous in absolute terms, perhaps millions of solar masses, but now moving through the dense gravitational medium of the host galaxy, without the surrounding structure that once made it feel massive to that medium. And here is the thing about Chandrasekhar's friction formula that matters enormously in this moment. The drag force scales with the mass of the moving object. A black hole embedded in a dense stellar nucleus, effectively inheriting the gravitational weight of everything around it, generates a far stronger wake than a naked black hole of the same intrinsic mass moving alone. Strip away the envelope and the friction drops. Not to zero. The black hole itself still has mass, still generates a wake, but to a level that may be wholly insufficient for the job remaining. The job remaining is sinking from several kiloparsecs out to the centre of a galaxy whose central regions are themselves dense and resistant. When you run the numbers, and this is where the result sits uncomfortably in the mind, the timescale for a stripped, naked black hole to sink from a few kiloparsecs to the galactic centre through dynamical friction alone can come out longer than the current age of the universe. Longer. Which means the black hole doesn't arrive, not in any time frame that astronomy currently has access to. It orbits, kiloparsecs from the centre, threading through the host galaxy's outer regions, too stripped to sink efficiently, too massive to be scattered away. A permanent wanderer, almost, or at minimum, a very long-term one. I find this result quietly unsettling in a way I didn't expect the first time I encountered it, because it means the galaxy carries this thing around, this invisible, massive, displaced object, and leaves no obvious trace of it on the surface. The galaxy looks complete from the outside. It looks like it has one central black hole where it should. And somewhere in its body, a few thousand light years from centre, something that should be there but isn't, is doing slow, lonely laps. The sinking timescale has simply run out of universe to finish in. Gravity does not pull evenly. This is the fact that makes tides possible. Not just ocean tides, not just the bulge of water on the side of Earth facing the moon, but tides in the broadest sense. The differential pulling that happens whenever a gravitational field stretches across an object with physical extent. The near side of that object sits closer to the source of gravity and feels a stronger pull. The far side sits further and feels a weaker one. The difference between those two pulls, not the gravity itself, but the difference, is what a tidal force actually is. For objects small enough, the difference across their diameter is negligible. A person standing on the surface of Earth feels essentially the same gravitational pull at their feet as at their head. The moon's tidal force across a human body is real but unmeasurable by any sensation available to us. But stretch the object out, make it a galaxy, or a satellite galaxy falling through the gravitational field of a larger one, and the differential becomes the dominant force shaping what happens next. The satellite galaxy doesn't experience its host's gravity as a single uniform pull. It experiences a gradient. The leading edge, closer to the host centre, gets pulled harder. The trailing edge gets pulled softer. And the satellite's own self-gravity, the internal glue holding its stars and gas and dark matter together, has to compete against that gradient at every point. Where the tidal gradient wins over self-gravity, material gets pulled away, not explosively, not all at once, but persistently and this is the only comparison that keeps forming, like a sweater catching on something and unravelling one thread at a time while you keep walking, unaware of what's coming loose behind you. The stars at the satellite's outer edges are the least gravitationally bound to it. They go first, then the outer dark matter halo, then progressively the layers inside, each orbital passage through the host galaxy's inner regions stripping another layer, bringing the tidal radius, the boundary within which the satellite can hold onto its own material, closer and closer to the satellite's core. This has a direct and quietly erosive effect on the SMBH sitting at that core. The black hole's ability to sink toward the host galaxy's centre depends, as the previous chapter traced, on the dynamical friction generated by the mass surrounding it. As tidal stripping removes that surrounding mass, it doesn't just reduce the black hole's effective gravitational weight in the medium, it also distorts the black hole's trajectory. The differential force across the remnant core pushes and pulls unevenly. The orbit, which might have been cleanly inward spiralling in the absence of tidal distortion, becomes lopsided, slightly eccentric. The black hole's path through the host galaxy shifts in ways that dynamical friction calculations for idealized, spherical, undisturbed systems don't fully anticipate. What tidal forces add beyond the mass stripping that chapters prior to this have already described is an ongoing perturbation to the trajectory itself. The SMBH is not just losing its gravitational cushion, it is being pushed fractionally off the path it would have taken. The displacement this causes is subtle. Over a single orbital passage, the deviation from an idealized inspiral might be small enough to seem unimportant. But orbital passages accumulate and deviations compound, and over hundreds of millions of years, the SMBH can end up on an orbit that would have required a fundamentally different set of initial conditions to explain if you encountered it cold. Galactic tides are not the loudest mechanism in this story. They don't announce themselves in the data with the clarity that a gravitational wave recoil event might, but they work continuously at every scale, across every merger, nudging trajectories, stripping mass, quietly relocating the point where the black hole ends up. The displacement accumulates the same way erosion does, not in moments, in time. At some point during a galaxy merger, the two galactic cores stop being separate things. It doesn't happen cleanly. There's no moment where you could draw a line and say, here, before this there were two nuclei and after this there is one. It happens gradually, then suddenly, the way most structural transitions in astrophysics seem to work. A long preparation, then a lurching commitment, then a new configuration that looks almost stable, but carries the memory of everything that came before it. The final pericentric passage is when this transition becomes irreversible. The two cores sweep through each other at their closest approach. Dense regions of gas and stars moving through a shared gravitational field that is, by this point, deeply asymmetric. The outer structure of the merger is already knotted with tidal tails and redistributed material. The dark matter halos have long since begun to overlap. What remains distinct, what still holds some structural identity, is the innermost region of each original galaxy. The dense nuclear gas, the stars closest to each central black hole, the compressed material that has been funneled inward by hundreds of millions of years of orbital interaction. And this material, this dense, compressed innermost stuff, is not symmetric. It was never perfectly symmetric, even before the merger began. Gas is fussy that way. It doesn't distribute itself in clean spherical arrangements. It clumps, it streams, it follows pressure gradients into filaments and voids, it responds to the radiation from nearby stars and the mechanical energy of supernova explosions in ways that make it inherently patchy and uneven. By the time two galactic cores are making their final approach, the gas distributions they carry are already lopsided, already carrying asymmetries accumulated over the entire merger history. Then turbulence arrives. The final pericentric passage drives shockwaves through the gas. When two dense regions of interstellar medium collide at the velocities involved in a galactic core encounter, hundreds of kilometers per second, the gas doesn't simply compress uniformly. It fragments. Small-scale turbulent eddies form at the interfaces between the colliding streams, and those eddies interact with each other in ways that are genuinely not predictable in detail. The turbulence is, and I want to be precise here because I initially reached for the word violent and then pulled back because it implies something more directed than what actually happens. More like a fussy, unresolvable disagreement between fluid elements that can't decide which way to move. Pressure here, fighting pressure there. Vortices forming and collapsing faster than any large-scale structure can respond to them. The symmetry of the gas breaks. What this means for the two black holes sitting inside these cores is specific and consequential. Before the final passage, each black hole was more or less centered in its own dense gas reservoir. After the turbulent disruption of the gas symmetry, each black hole gets injected into the newly forming nuclear disk at a different position, with a different velocity, and with a different orbital energy than it would have had if the gas had behaved uniformly. One black hole might find itself nearly centered in the new nuclear disk, embedded close to the forming gravitational minimum, with conditions favorable for further sinking. The other might be injected with an apocenter, a furthest point in its new orbit, of 100 parsecs or more, swinging wide through the forming nuclear disk on an orbit that dynamical friction will need a long time to tighten. The difference between those two outcomes comes down to a few small asymmetries in the gas distribution at the moment of closest approach. Small causes, large consequences. What's strange about me, and I keep returning to this, is that the gas doesn't know it's making a decision about where the black holes end up. It's just following pressure gradients, responding to turbulent forcing, doing what gas does, but the black holes remember where they landed. And the nuclear disk that forms around them remembers too, in the shape of its density, in the warmth of its inner regions, in the uneven distribution of star formation that will persist for hundreds of millions of years after the gas that caused it has long since been consumed. There is a point in the inspiral where something shifts, not dramatically, not with any observable signal that would announce itself to a telescope pointed at the right galaxy, just a threshold crossed quietly in the mathematics of two massive objects moving through a shared gravitational field, after which the relationship between them changes in a particular and irreversible way. Before that threshold, each black hole is bound primarily to the galaxy. Its orbit is an orbit around the combined gravitational potential of stars, gas, dark matter, the whole merged system, with the other black hole just one contributor among many to the field it moves through. The two black holes are approaching each other, yes, drawn inward by the patient work of dynamical friction described in earlier chapters, but they are not yet. And this distinction matters more than it might initially seem, gravitationally committed to each other specifically. Then the separation closes enough. At roughly the scale of the black hole's mutual gravitational influence radius, the distance within which each black hole's own gravity begins to dominate over the galaxy's background potential, the two objects lock into a genuine binary. The influence radius for a supermassive black hole depends on its mass and the velocity dispersion of surrounding stars. But for typical systems, we are talking about separations somewhere between a few parsecs and perhaps 10. A parsec is about 3.26 light-years. The entire distance from Earth to the nearest star, Proxima Centauri, is just over 4 light-years. So we are discussing two objects, each containing millions or billions of solar masses, separated by a distance comparable to... comparable to the emptiness between us and our nearest neighbour. And at that distance they find each other. The dynamics change when this happens. Before binary formation, the relevant friction was the large-scale kind, dark matter halo drag, stellar dynamical friction operating across kiloparsec distances, the broad gravitational medium of the merged galaxy, doing the work of drawing the two centres together. After binding, the relevant physics becomes orbital. The two black holes are now moving around their common centre of mass. And what determines how that orbit evolves is no longer primarily the galaxy-scale medium, but the population of stars and gas in the immediate vicinity of the binary itself. There is something particular. I keep reaching for the word intimate, but it doesn't quite land, so perhaps just particular, about this transition. Two objects that spent hundreds of millions of years falling toward each other through an enormous shared gravitational landscape and then arrive at a separation of a few light-years and become effectively a single gravitating system orbiting itself. The binary at this stage has a hard, fast, elliptical quality to its orbital motion. The two black holes sweep around their common centre of mass in periods that can range from thousands to millions of years, depending on the separation and combined mass. The orbit may be eccentric, not a clean circle, but a stretched ellipse, each body accelerating as it approaches closest approach and slowing as it swings outward. Think of two stones attached by a shortening cord, swinging around each other in the dark, each one feeling the pull of its partner more clearly now than it has felt anything else in the last billion years. The galaxy continues around them. Stars orbit, gas flows, dark matter drifts, but the binary now formed has a different agenda. It is no longer falling, it is orbiting, and orbiting systems do not naturally spiral inward without something to carry the energy away. What carries it away next is the subject of considerable scientific discussion, and the answer, when it finally came, was both elegant and troubling. There is a particular kind of problem in physics that isn't really a problem with the physics. The equations are right, the mechanisms are understood. The individual pieces, dynamical friction, stellar scattering, gravitational wave emission, are each well described, each experimentally and observationally supported, each grounded in decades of careful theoretical work. The problem is that when you put those pieces together and ask what happens to a binary supermassive black hole at a separation of roughly 1 parsec, the answer comes back as something close to nothing. The binary stalls. It sits there, two objects containing between them perhaps billions of solar masses, separated by a few light years, and the universe seems to run out of mechanisms to bring them closer. This is, depending on your disposition toward open problems, either quietly maddening or quietly beautiful. I have spent enough time with it to feel something of both. To understand why the stall happens, you have to understand what got the binary to 1 parsec in the first place and what that journey cost. The inspiral from kiloparsec separations down to parsec scales was driven, as the preceding chapters described, by dynamical friction, the gravitational wake that a massive object generates in the surrounding medium, which pulls it backward and bleeds off orbital energy. For this to work, there need to be things in the medium. Stars, gas, dark matter particles, a dense enough background that the wake forms and the drag accumulates. During the early inspiral, the merged galaxy provides this medium abundantly. There are stars everywhere. The friction is efficient. The binary hardens, the term astronomers use for the progressive tightening of the orbit, at a reasonable pace. But the binary is not just passively moving through this stellar medium. It is doing something to it. Every time a star passes close to the binary, it undergoes a three-body gravitational interaction. It gets flung away, ejected at high speed, transferring some of its kinetic energy to itself and carrying that energy out of the system. This is the slingshot mechanism, and it is, in its way, the binary doing the work of hardening itself, extracting energy from its own orbit and depositing it into the surrounding stellar population. The stars that get ejected carry energy outward. The binary, having given that energy away, tightens slightly, efficient, for a while. The smell of old paper comes to mind for some reason when I think about the next part. Something about the texture of a problem that's been sitting unresolved in the literature for decades, annotated and worried over and approached from every direction without quite being solved. Because here is what happens to the stellar population as the binary ejects stars. It depletes it. The stars that are on orbits passing close enough to the binary to interact with it, what theorists call the loss cone, the region of orbital phase space that feeds stars to the binary, those stars get ejected. And the loss cone, once emptied, refills slowly. In a spherically symmetric galaxy, the rate at which new stars scatter into the loss cone is low, lower than the rate at which the binary ejects them. So the binary runs through its available fuel supply and finds itself sitting in a region of space that it has, over millions of years, systematically cleared of the very stars it needs to keep hardening. This is not a failure of any individual mechanism. It is a structural consequence of the binary doing its job too well in too small a space. At roughly 1 parsec, the stellar medium within reaches threadbare. Dynamical friction from the remaining diffuse gas and dark matter exists, but it is residual, a whisper of the drag that operated at kiloparsec scales. Not nothing, but not enough. The binary's orbital velocity at this separation is high enough that even what friction remains can barely register against the momentum of two objects this massive moving this quickly. And gravitational waves, or the mechanism that will eventually drive the final coalescence, are not yet significant at 1 parsec. Gravitational wave power scales steeply with separation, growing enormously as the two objects get closer. At a parsec, the time scale for gravitational wave in spiral is longer than the age of the universe. The binary has not yet reached the regime where gravity's own radiation can do the closing work. So it stalls two objects, billions of solar masses between them, separated by a few light years. And the universe, at this scale, appears to have run out of things to say. The problem carries an uncomfortable implication. If binaries truly stall and never merge, then the gravitational wave signals we'd expect from these coalescences, signals that pulsar timing arrays have now begun to detect in the low-frequency gravitational wave background, should not exist in the abundance we observe. But they do exist, which means something is resolving the stall, something is bridging the final parsec. And the current best answers to what that something might be are partial, contested, and in places genuinely uncertain. The stall is probably not permanent. The problem is probably not the problem it looks like. But probably is doing a lot of work in that sentence, and everyone in the field knows it. The binary doesn't wait. Even as it stalls at the parsec scale, even as the mechanisms driving its in spiral begin to thin and lose their grip, the binary is still doing something, still reaching outward, still interacting with whatever passes close enough to feel its gravitational pull. And what passes close enough in the dense nuclear region of a recently merged galaxy is stars. Stars on certain orbits that bring them looping through the inner regions of the galaxy, dipping close enough to the binary's gravitational sphere of influence to get caught in a three-body interaction. Those stars do not simply continue on their way. A three-body gravitational encounter, when one of the bodies is a tightly bound binary of objects each weighing millions of solar masses, is not a gentle deflection. The star enters the interaction with some velocity, some orbital energy. It leaves with considerably more. The binary gives the star a kick, flings it outward. The star rockets away from the galactic nucleus at speeds that can reach hundreds or even thousands of kilometers per second, and fast enough in some cases to escape the galaxy entirely. These are hypervelocity stars. They have been observed. Some of the high-velocity stars detected in the outer Milky Way are thought to carry the record of exactly this kind of encounter, though proving the origin in any individual case is genuinely difficult. But here is the part that matters for the binary itself. Energy is conserved. When the star leaves with more kinetic energy than it arrived with, that energy came from somewhere. It came from the orbital energy of the binary, so from the motion of the two black holes around each other. Every ejected star carries a small slice of that orbital energy away with it, and the binary, having given that energy away, finds itself in a slightly tighter orbit, a slightly smaller separation, harder in the technical sense. A harder binary is a more tightly bound one that has paid for its compression in the currency of flung stars. The hardening is real. The mechanism works. It just requires a continuous supply of stars willing, wrong word, stars aren't willing, they're just on the wrong orbit at the wrong moment, available. And availability is the constraint. The loss cone, the region of orbital phase space containing stars on trajectories that intersect the binary's influence, has a finite population. Stars get ejected faster than new ones scatter in from the broader galactic nucleus. The supply thins, the hardening slows. This is the thread that connects back to the final parsec problem and the depletion it describes, not a separate phenomenon, but the same one viewed from inside. What remains after years, after millions of years, of this process is a galactic nucleus with a hollowed center. Not physically empty, stars are still there, but depleted. The stars that were on the orbits most likely to interact with the binary have been flung out. What's left are the stars on safer orbits, further out, less likely to dip into the binary's reach. And the light those remaining stars produce, mapped carefully with a telescope, shows a deficit relative to what you'd expect from a simple extrapolation of the outer stellar density profile inward. Astronomers call these structures cores, regions at the centers of massive elliptical galaxies where the stellar brightness profile flattens out rather than continuing to rise toward the nucleus, scooped shallow by a history of binary ejections. They are not absences, not holes, just thinning, a place where something heavy once sat and worked and left a record of its labour in the distribution of what it didn't touch. The mass of the core deficit, the difference between the observed stellar mass and what the outer profile would predict, correlates across many galaxies with the mass of the central black hole. The heavier the binary that once operated there, the larger the scooped region. You can read the black hole's history in the shape of the light around it. That's the part that stays with me. A mechanism invisible in real time, operating over millions of years, leaving a record written in stellar brightness that persists for billions more. The stars were the fuel, the core is the receipt. Something concentrates around a growing black hole. It happens slowly, over the same timescales on which the black hole itself accumulates mass. Millions to billions of years of gradual growth, gas falling inward, accretion disks spinning, mass building increment by increment. The black hole doesn't grow in isolation, it grows inside a dark matter halo, and as it grows, its deepening gravitational potential reaches outward into that halo and rearranges what it finds there. Dark matter particles, responding to the slowly strengthening gravity of the growing black hole, migrate inward. Not all of them. The effect is strongest close to the nucleus, weaker further out, but close in the dark matter density steepens. What was a relatively smooth distribution develops a concentration, a region of elevated density clustering around the black hole-like, and there is really only one image that holds this properly, like sediment accumulating at the lowest point of a slow drain. Not deposited suddenly. Built up over an enormous span of time layer by layer, each layer responding to the gravitational preference created by what accumulated before it. This is what physicists call a dark matter spike. It isn't a physical protrusion. It has no surface, no boundary you could identify by crossing it. It is purely a density feature, a region where the dark matter is more concentrated than it would be in the absence of the black hole's long growth history. But density is gravitational mass per unit volume, and mass generates friction, and friction acts on anything moving through it, including a Session black hole trying to close the final parsec. Here is why this matters for the stall described in the previous chapter. The binary has depleted its stellar loss cone. Dynamical friction from the remaining stars is residual, threadbare, insufficient to drive further hardening on any astronomically relevant timescale. But the dark matter spike, accumulated over the entire lifetime of the black hole, independently of the stellar dynamics, and therefore not subject to the same depletion, is still there. Still dense, still capable, in principle, of generating drag on the orbiting binary. Whether it actually does depends critically on the nature of the dark matter itself. In the standard model of cold, collisionless dark matter, particles that interact with each other, and with ordinary matter only through gravity, the spike faces a problem. As the binary hardens and the two black holes move faster and faster through the inner region, the energy they deposit into the spike through dynamical friction begins to disrupt it. The spike heats up, in a gravitational sense. The dark matter particles that were concentrated there get scattered into higher energy orbits. The very friction that was supposed to help the binary cross the final parsec ends up destroying the structure providing that friction. Collisionless cold dark matter, in this scenario, cannot fully bridge the gap. It tries, and in trying dismantles itself, but self-interacting dark matter behaves differently. If dark matter particles can interact with each other, not through electromagnetism or the strong force, but through some new, weakly coupled interaction, perhaps mediated by a dark photon, then the spike responds differently to being heated. Self-interactions allow the spike to redistribute energy among its own particles more efficiently, maintaining a denser, more isothermal core rather than fragmenting under the energy input from the binary. The friction persists, the bridge holds. In 2024, a paper published in Physical Review Letters argued that self-interacting dark matter with an interaction cross-section of roughly the right magnitude could supply exactly this sustained friction, enough to carry the binary from 1 parsec down to the scale where gravitational wave emission takes over, and to do so on timescales consistent with the observed universe. The same model, the authors noted, produces a gravitational wave background spectrum that matches what NANOGrav reported in 2023. That alignment between a proposed dark matter property and an observed gravitational wave signal is the kind of thing that makes careful physicists pause, without quite committing. It might be the bridge, it might be something else providing the bridge, and this being a coincidence of constraints. The uncertainty is real, and anyone telling you otherwise is working ahead of the data, but the spike is there. And the question it raises, what kind of dark matter allows it to do its job, is not a small one. There is something about a stone skipping across water that resists easy explanation. You know the mechanics, roughly. The angle of entry, the spin, and the way the flat face of the stone meets the surface tension of the water and generates a brief upward force before the stone becomes briefly airborne again. You understand it. But watching it happen, the irregular bounce, the unpredictable spacing between skips, the way the stone doesn't follow a clean arc but lurches and stutters across the surface, it still looks like the stone is doing something slightly wrong, like it's failing to sink the way it should. A supermassive black hole moving through a halo of ultralight dark matter can behave something like that. Not because the physics is the same, it isn't. But the outcome, an object that should by straightforward logic be sinking uniformly toward the centre of a gravitational potential, instead bouncing and lurching along an unsteady stochastic path that resists simple prediction, carries that same quality of wrongness, of something failing to do the obvious thing. Ultralight dark matter, sometimes called fuzzy dark matter, is a proposed alternative to the standard cold dark matter particle. Instead of being composed of relatively heavy, slow-moving particles that cluster in smooth halos, fuzzy dark matter is built from particles so extraordinarily light, with masses perhaps 20 orders of magnitude smaller than an electron, that their quantum mechanical wave nature operates not at subatomic scales, but at the scale of entire kiloparsecs. These particles have de Broglie wavelengths long enough to span the central regions of galaxies. Their quantum behavior isn't a microscopic detail, it is the large-scale structure. At the center of a fuzzy dark matter halo, something forms that has no analogue in classical dark matter models. A soliton, a stable self-sustaining wave structure, held together by the balance between quantum pressure pushing outward and gravity pulling inward, sitting at the gravitational minimum like a dense, oscillating core. Not a solid object, not a particle cluster. Something more like a standing wave in the dark matter density field, breathing in and out on the timescales of millions of years, and this soliton is not quiet. Even in the absence of external disturbances, the soliton oscillates, its density fluctuates, its central position shifts slightly, jittering around the gravitational minimum in ways that are, and I want to be careful here because calling it random undersells the structure, irregular and wave-driven, following a pattern that emerges from quantum interference rather than from any classical randomness. A supermassive black hole sitting in or near this soliton doesn't experience a smooth static gravitational potential. It experiences a potential that is breathing, shifting and oscillating on timescales comparable to its own orbital period. The dynamical friction it feels is no longer a simple predictable drag proportional to the local density. The soliton's collective response to the black hole's presence, the way the entire wave structure reorganizes around the incoming mass, can generate something that in certain regimes acts more like a push than a pull. Negative friction. The soliton briefly accelerating the black hole rather than slowing it. When this happens, the black hole doesn't sink. It skips, it approaches the center, feels the soliton reorganize around it, gets deflected or even slightly pushed outward, swings away, falls back in, and the cycle repeats with just enough irregularity that no clean and spiral trajectory forms. The stone skips across the surface instead of sinking through it. Whether real dark matter is fuzzy remains genuinely unresolved. The model makes predictions, about the inner density profiles of dwarf galaxies, about certain features in the matter-power spectrum that observations are still in the process of testing with results that are mixed enough to keep the question open. It might be fuzzy, it might not be, it might be something else entirely. But the stone-skipping problem it describes is real within the model, and the model is alive enough scientifically that it cannot simply be set aside, which means the question of whether a supermassive black hole reliably sinks to the centre of its host galaxy, a question that seems, from the outside, like it should have an obvious answer, turns out to depend on what dark matter is, and that still we do not know. When two black holes finally merge, they do not do it quietly. The last few orbits before coalescence are the most energetic events in the observable universe. Two objects of extraordinary mass moving at a significant fraction of the speed of light, spiralling inward on a timescale that compresses from thousands of years to seconds as the separation collapses, radiating gravitational waves with a luminosity that can briefly exceed the combined light output of every star in the observable universe. The merger is, in its final moments, a release of accumulated gravitational potential energy so complete that the two original objects cease to exist as distinct things and become, in an instant that general relativity describes with uncomfortable precision, a single spinning remnant. But something happens in that instant that is easy to overlook. The gravitational waves carry momentum. Not just energy, not just angular momentum, linear momentum. And linear momentum is conserved. If the merged system radiates linear momentum preferentially in one direction, if the gravitational wave emission is lopsided, stronger in one direction than another, then by conservation, the remnant black hole must recoil in the opposite direction. It gets kicked. Not by any external force, not by any collision, but by the asymmetric pattern of its own gravitational radiation. This is the recoil, and it follows from nothing more exotic than Newton's third law, extended into the language of general relativity. The question then is what makes the emission lopsided? Perfect symmetry would produce no kick. If two identical black holes, non-spinning of exactly equal mass, merged in a perfectly symmetric configuration, which is, admittedly, a scenario that never occurs in nature with literal exactness, but approach it and the kick approaches zero. The gravitational wave emission from a perfectly symmetric merger has no preferred direction. The radiation goes equally in all directions. No net linear momentum is carried away, no recoil. Break the symmetry, and the kick appears. The first way to break it is mass. When two merging black holes have unequal masses, one heavier, one lighter, the orbital dynamics of the inspiral are asymmetric. The lighter black hole moves faster, traces a wider arc, contributes differently to the gravitational wave pattern than the heavier one. The emission becomes directionally lopsided in a way that scales with the mass ratio. The more unequal the masses, the stronger the asymmetry, up to a point. For non-spinning black holes, the maximum kick from mass asymmetry alone reaches roughly 170 kilometers per second. That's significant, but it isn't the whole story. The second way to break symmetry is spin. And spin, the intrinsic angular momentum of each black hole, does something to the kick that mass ratio alone does not approach. When both black holes are spinning, their spins interact with the orbital angular momentum of the binary in ways that are, to put it plainly, fussy. The precise orientation of each spin relative to the orbital plane, relative to each other, relative to the direction of inspiral, all of it feeds into the final radiation pattern. The gravitational wave emission from a spinning binary merger has a directionality that emerges from the three-dimensional geometry of the spin configuration, and that geometry can, in certain arrangements, produce kicks far beyond anything mass asymmetry generates. For typical spin configurations, the recoil velocity sits somewhere in the range of a few hundred to perhaps 1,000 kilometers per second. Already enough, as described in the next chapter, to significantly displace a merged black hole from the center of most galaxies. But there are configurations, specific, rare, requiring particular spin orientations that do not commonly arise, where the kick reaches much higher. The remnant black hole, in those cases, does not wander. It runs. What is strange about all of this, sitting with it now, is that the kick is not an anomaly. It is not a quirk or a pathological edge case. It is the generic outcome of merging two objects that are, in any realistic astrophysical scenario, not perfectly symmetric. Which means every SMBH merger in the history of the universe has produced a recoil. Every one. The merged remnant was displaced from the centre it occupied before the coalescence by some amount in some direction at some velocity. The only question is whether the galaxy could hold on to it. Not every merger produces the same kick. The recoil velocity, that sideways shove delivered to the merged remnant by its own lopsided gravitational wave emission, depends entirely on the geometry of what went into the merger, the masses, the spins, and most critically, the orientation of those spins relative to each other and relative to the orbital plane in the final moments before coalescence. Most mergers produce kicks in the range of a few hundred kilometers per second. Significant enough to displace a black hole from a galactic nucleus, significant enough to send it wandering for hundreds of millions of years, but not, in a massive galaxy with a deep gravitational potential, necessarily enough to escape entirely. Then there is the particular configuration that produces the superkick. The setup requires two black holes spinning at or near their maximum rate. Maximally spinning or close to it, what physicists describe using a dimensionless spin parameter that runs from 0 for a non-spinning hole to 1 for the theoretical maximum. And the spins need to be oriented in a specific way, both lying in the orbital plane, pointing in opposite directions, anti-aligned. One spinning clockwise as seen from above the orbital plane, the other spinning counterclockwise, both spins horizontal rather than vertical relative to the orbit. This configuration is geometrically particular in a way that is hard to convey without the mathematics. But the intuition runs something like this. The gravitational wave emission from a merging binary has a directionality that depends on how the system's angular momentum is distributed. When the spins are aligned with the orbital angular momentum, both pointing up or both pointing down, the emission pattern has a certain symmetry that limits how lopsided it can become. When the spins are anti-aligned and lying in the orbital plane, that symmetry breaks in the most extreme way available to the system. The radiation patterns becomes as lopsided as general relativity permits. The result is a recoil velocity that can reach approximately 5,000 kilometers per second. The name Superkick, by the way, reminded me immediately of Shawn Michaels' HBK, and I went down that rabbit hole for longer than I probably should have. His match with The Undertaker at WrestleMania 25 is still one of the best things I have ever watched. The Undertaker catching the moonsault and converting it directly into the tombstone to take the win. I remember just sitting there. Anyway, that has nothing to do with black holes. Back to the physics. 5,000 kilometers per second. To put that in context, the escape velocity from a dwarf galaxy is roughly 10 kilometers per second. From a galaxy like the Milky Way, it sits somewhere around 500 to 600 kilometers per second, depending on where in the halo you are measuring from. From a giant elliptical galaxy, one of the most massive systems in the universe, escape velocity can reach perhaps 1,000 kilometers per second. A superkick of 5,000 kilometers per second exceeds the escape velocity of essentially every galaxy type we know of. A merged black hole receiving that kick does not wander. It leaves. It exits the host galaxy entirely, carries its accretion disk remnants with it into intergalactic space, and becomes something the universe has no clean category for. A black hole between galaxies, belonging to nothing, orbiting nothing, drifting through the void on a trajectory that will not curve back for billions of years, if ever. The superkick is rare. The spin configuration required does not arise in every merger, or even most of them. For it to occur, The two black holes need to have arrived at coalescence with their spins in that particular anti-aligned in-plane geometry, a configuration that gas dynamics and spin-orbit coupling tend to work against, gradually aligning spins with the orbital angular momentum over the inspiral. Nature has mechanisms that make the superkick less likely, but not impossible. The configuration can survive if the inspiral is dry enough, gas poor, with little accretion to gradually align the spins. In those mergers, the spin geometry entering coalescence is closer to random, and random occasionally lands on the configuration that produces 5,000 kilometers per second. The merged remnant in those cases is gone before the galaxy has time to respond. Escape velocity is not a speed limit, it is a threshold. The minimum speed an object needs to carry away from a gravitational source in order to never return, assuming no further propulsion, no additional forces, nothing pushing or pulling after the initial launch. Below that threshold, whatever was thrown comes back eventually. Above it, the object moves outward forever, its speed decreasing asymptotically but never quite reaching zero, the gravitational pull behind it weakening with distance but never fully releasing its grip. What varies enormously from one galaxy to the next is where that threshold sits. A dwarf galaxy, the small, faint, low-mass companions that orbit larger systems in abundance, the kind of galaxy that gets absorbed in minor mergers of the sort described earlier, has a shallow gravitational potential. Its escape velocity from the central region is roughly 10 kilometers per second. In some of the smallest dwarf galaxies, even less. 10 kilometers per second is fast by everyday standards, about 30 times the speed of sound in air, but in the context of black hole merger kicks, it is almost nothing. A typical merger recoil of a few hundred kilometers per second exceeds it by 2 orders of magnitude. In a dwarf galaxy, almost any kick from almost any merger configuration sends the merged black hole out and over the threshold, permanently. This has a specific and uncomfortable implication for the growth histories of black holes in small galaxies. Every major merger in principle risks ejecting the product. The black hole that forms when 2 smaller holes combine may simply leave. The galaxy then rebuilds from whatever black holes remain, or begins again from a smaller seed, or, in the most extreme cases, ends up with no central black hole at all for an extended period. A galaxy that keeps losing its black holes to recoil is a galaxy that struggles to grow one. The Milky Way sits in a different regime. Our galaxy's escape velocity from the central region is somewhere between 500 and 600 kilometers per second, depending on how you model the dark matter halo and where exactly you're measuring from. A typical merger kick of a few hundred kilometers per second bores, the kind produced by mass asymmetry and moderate spin misalignment, falls below this threshold. The merged remnant doesn't escape, but it doesn't stay put either. It wanders. A kick of, say, 300 kilometers per second in a galaxy, with an escape velocity of 550 sends the black hole on a long, looping orbit through the galaxy's body. The black hole swings outward, slows as gravity pulls it back, swings inward, overshoots the center, swings outward again. Each pass brings it through regions of varying density and dynamical friction, thin, sluggish compared to what it was before the merger cleared the nucleus, gradually bleeds off orbital energy. The wandering damps down. Eventually, over hundreds of millions to perhaps 1 billion years, the black hole settles back towards center. Probably. The word is doing real work there, because the settling timescale depends on how much material is left to generate friction after the merger scooped the nuclear region clean. And then there are the giant ellipticals. These are the most massive galaxies in the universe, typically sitting at the centers of galaxy clusters, built from dozens or hundreds of mergers over cosmic history. Their escape velocities from the central region can reach 1,000 kilometers per second or beyond. Even a substantial kick, 500-600 kilometers per second, keeps the black hole bound. The wandering orbit is shorter, the return faster, the galaxies grip firm enough that only the most extreme spin configurations produce a genuine ejection risk. The same kick that liberates a black hole from a dwarf galaxy barely disturbs a giant elliptical's center. Gravity doesn't negotiate. It just holds, or doesn't, based on numbers that were set long before the merger happened. Two black holes in a binary have, in a limited sense, a predictable future. Not certain, the final Parsec problem makes clear that the path from binary to merger is neither guaranteed nor simple, but bounded. The two objects orbit each other, interact with their stellar environment, harden slowly or stall, and the outcome space, while uncertain in detail, has a shape you can describe. Either they eventually merge, or they don't. The binary either closes, or it doesn't. The system has two players and a fixed set of rules. Add a third, and the rules stop being fixed. This is not a metaphor. The three-body gravitational problem is one of the oldest unsolved problems in classical mechanics, not unsolved in the sense that we lack equations for it, but unsolved in the sense that those equations cannot be integrated analytically for generic initial conditions. Three massive objects interacting gravitationally produce a trajectory that is, in the technical sense, chaotic. Not random. The system is fully deterministic, but sensitive to initial conditions in a way that makes long-term prediction practically impossible. Shift the starting position of any one of the three objects by an arbitrarily small amount, and the eventual outcome of the encounter changes completely. What happens then when a third supermassive black hole arrives at a galactic nucleus, where a binary already exists? The arrival happens because galaxy mergers are not isolated events. A galaxy that has already absorbed one companion already has a binary sitting in its nucleus from that first merger, does not stop existing in a universe full of other galaxies. A second merger can begin while the first binary is still hardening, a third galaxy falling in, its own central black hole descending through the merged system's potential well, arriving at the nucleus before the original binary has had time to coalesce. The third black hole drops into the binary's gravitational domain, and the encounter that follows is structurally ungainly in a way that two-body dynamics never is. The three objects begin a close gravitational interaction. The binary, and the two original black holes already in an established orbit, acts, in a rough sense, as a unit with a combined gravitational potential and a characteristic binding energy. The third intruder, falling in from outside, brings kinetic energy from its inspiral. When the intruder gets close enough to the binary to feel its detailed gravitational structure, close enough that the tidal field of the binary, not just its combined mass, is influencing the intruder's trajectory, the interaction becomes genuinely three-body. What typically follows is an exchange of energy that favours a specific outcome. The lightest of the three objects tends to be ejected. Not always. Three-body encounters have no strict rule that guarantees this, and simulations show a range of outcomes. But the statistical weight of many simulated encounters points consistently toward the least massive participant receiving the largest velocity kick and being expelled from the system. The two heavier objects, having given energy to the lighter one in the exchange, find themselves in a tighter, more bound orbit than before. The slingshot, in other words, hardens the binary while removing its third wheel. The ejected black hole, lighter, faster, leaves the nucleus at a velocity that can exceed what gravitational wave recoil would typically produce. Slingshot kicks can reach higher velocities precisely because the energy source is different. Not the gravitational wave emission from the merger itself, but the orbital binding energy of the binary, which is large and available. Whether the ejected object escapes the galaxy depends, as with recoil kicks, on the galaxy's escape velocity and the mass ratio of the encounter. What distinguishes the slingshot aftermath from a recoil event is less about velocity and more about what remains. After a gravitational wave recoil, there is one merged remnant and nothing else at the nucleus. After a slingshot, the nucleus retains two black holes, the hardened binary, potentially close enough now to merge on a short timescale. Their orbit tightened by the energy they transferred to the departing third object. Two signatures. Two black holes left behind, or one. That distinction, sitting in the data if you know to look for it, is how these mechanisms, in principle, can be told apart. In practice, the data is rarely that clean. But the principle holds, even when the observations blur it. There is a difference between something that doesn't exist and something that cannot be seen. It sounds obvious when stated plainly. But in astronomy, where existence and detectability are so thoroughly entangled, where we know about things almost exclusively because they emit or absorb or deflect light in some way we can measure, the distinction carries more weight than it might seem. A displaced supermassive black hole drifting through the body of its host galaxy is not absent. It is not a ghost or a remnant or a memory of something that was once there. It is fully, physically present. Millions or billions of solar masses of curved spacetime moving through the galaxy at a speed set by the kick or the stripped-in spiral that displaced it, and it is, in the absence of accretion, entirely invisible. Not dim, not faint, invisible. A black hole accretes when material falls into it. Gas, disrupted stars, the accumulated debris of a dense environment, and the gravitational energy released in that accretion heats the infalling material to temperatures that produce X-ray emission, radio jets, optical luminosity. This is what makes active galactic nuclei bright. This is what lets us see supermassive black holes at cosmological distances, in galaxies billions of light years away. The black hole itself emits nothing. What we see is always the consequence of feeding. A wandering black hole drifting through the outer regions of a galaxy it was displaced from, or through the intermediate regions of a galaxy whose nuclear feeding ground it no longer occupies, is not feeding. Not substantially. The gas densities in the regions it passes through are too low, too diffuse, to sustain meaningful accretion. The interstellar medium it drifts through is thin. There is enough hydrogen there to fill a room with something that smells like nothing at all and weighs almost as much as nothing. And it is through stuff like that, genuinely thin, genuinely sparse, that the black hole moves, accreting at a rate so low it produces no detectable signal. It is just moving. And the forces still acting on it are real, if weak. The galaxy's gravitational potential continues to shape its trajectory. The black hole is not in free space, not beyond the reach of the galaxy's gravity, but orbiting within it on a path set by the initial displacement velocity and subsequently shaped by the distributed mass of stars and dark matter through which it passes. Dynamical friction, thin and residual in the low-density outer regions, continues to bleed off energy at a rate far slower than it operated in the nuclear region, but not zero. The orbit is not fixed. It is slowly, unhurriedly evolving, each pass through the inner regions of the galaxy depositing a small fraction of kinetic energy into the surrounding medium, each swing outward, carrying it through gas too sparse to notice it has passed. The wandering can last a long time. Simulations that track displaced black holes through realistic galaxy potentials find wandering timescales that range from hundreds of millions to several billion years, depending on the kick velocity, the galaxy's mass distribution, and the density of the medium available to generate friction. Some black holes return to the center relatively quickly, their orbits damped efficiently by a dense, gas-rich post-merger environment. Others persist as wanderers for timescales that approach or exceed the current age of the universe, their orbits decaying too slowly to bring them home within any time frame that feels finite. What the black hole is doing during all of this is, in a sense, nothing special. It is being a massive object in a gravitational field. It curves space-time around itself as it always has. Stars that pass within its influence radius feel its gravity and deflect slightly from their previous paths. Not dramatically, not in ways that would register as an obvious signal to a distant observer, but perceptibly in principle if you knew precisely where to look and had the astrometric precision to measure the effect. It exists, it influences, it drifts. The moment it becomes detectable again is not something the black hole controls or initiates. It's a matter of circumstance, of a star wandering onto the wrong orbit, or a gas cloud drifting into the region where the black hole's tidal forces become significant, or a chance alignment that puts the black hole between a background source and our line of sight long enough for gravitational lensing to briefly betray its position. The wanderer doesn't announce itself. It waits, without intention, for the universe to accidentally reveal it, and mostly the universe doesn't. The number, when you first encounter it, seems like it should be wrong. Not dramatically wrong, not off by a factor of 1,000,000, not a typographical error, just quietly, stubbornly inconsistent with the picture most people carry of what a galaxy looks like. A galaxy has a central black hole. One, at the centre. This is the assumption built into decades of textbook diagrams and popular science descriptions and the mental model that forms naturally when you hear the words supermassive, black hole and galaxy used together. One per galaxy, at the centre. The Romulus 25 cosmological simulation suggests the actual number for a galaxy the mass of the Milky Way is closer to 12. Romulus 25 is worth describing briefly before its results are leaned on, because the results only mean something if the method is capable of producing them. Most large-scale cosmological simulations handle black holes by anchoring them, fixing them artificially to the centres of their host halos, or snapping them back to the halo centre when they drift too far. This is computationally convenient and produces reasonable results for many questions, but it makes the simulation structurally incapable of tracking what actually happens to black holes that get displaced. It erases the wanderers by construction. Romulus 25 was built differently. It was specifically designed to capture the orbital evolution of black holes during and after galaxy mergers, tracking their trajectories through the simulated gravitational potential with sufficient resolution to follow them to sub-kiloparsec accuracy. Black holes in Romulus 25 are not pinned. They are allowed to drift, to stall, to wander, to fail to return. The simulation does not assume the answer. It computes it. And what it computes, for a sample of Milky Way mass halos, is an average of 12.2 wandering supermassive black holes per galaxy, above 1 million solar masses each, distributed throughout the virial radius, not counting those still sitting in satellite halos that haven't yet been fully absorbed. Within just the inner 10 kiloparsecs from the galactic centre, the average is 5.1, not 1, 5. The wanderers in the simulation are not randomly distributed through the galaxy. They are preferentially found outside the disk, in the halo, in the outer regions, in the spaces between the visible structures. This is consistent with their origin. Most of them are the former nuclei of smaller satellite galaxies, accreted in the early universe when the merger rate was higher and the galaxy was still assembling itself. They fell in, lost their stellar envelopes, stalled in their in-spiral, and have been orbiting ever since. Some of them have been wandering for several billion years. They are not recent. They are old residents, invisible and unannounced. Now scale this up. The number of wandering SMBHs scales roughly linearly with halo mass in the Romulus simulations. A galaxy twice as massive as the Milky Way hosts roughly twice as many wanderers. The relationship is not perfectly linear, yisumnium. There is scatter, and the physics of individual merger histories introduces variation, but the trend holds across the mass range explored, which means that for the most massive structures in the universe, the implications become, in the most understated way I can manage, quietly staggering. A galaxy cluster, a structure containing hundreds to thousands of individual galaxies, with a total halo mass perhaps 10,000 times that of the Milky Way, is predicted by the Romulus cluster simulation to harbour up to 1,613 wandering supermassive black holes within its main halo alone. 1,600 black holes, each above 1,000,000 solar masses, drifting through the intra-cluster medium and the halos of member galaxies, invisible, unaccreting, doing nothing detectable. The mass locked up in wandering black holes is not trivial either. At the current epoch, wanderers account for roughly 10% of the total black hole mass budget in a Milky Way mass galaxy. 10% of the mass in black holes is not sitting at the centre doing what we expect it to do. It is distributed, spread through the galaxy's body, accumulated from a history of mergers and displacements that the galaxy carries no obvious record of on its visible surface. Go back further in time and the fraction grows. At redshifts above 3, in the early universe, when the merger rate was higher and fewer black holes had settled, the total luminosity budget of accreting black holes was dominated not by central AGN, but by wanderers. The hidden population was like briefly the dominant one. That detail settled into me slowly, and I'm still not sure I have fully absorbed it. The black holes we point to when we talk about supermassive black holes, the ones at the centres of galaxies, the ones in the famous images, may represent the organised minority. The rest are out there, drifting, uncounted. Finding something that produces no light is, by definition, an indirect business. You cannot point a telescope at a wandering supermassive black hole the way you point one at a star or a nebula or an active galactic nucleus. There is nothing to point at. The black hole is there, massive, real, curving space-time around itself as it drifts. But without accretion, without a fuel supply, it radiates nothing across any part of the electromagnetic spectrum. Detection requires waiting for the universe to accidentally put something in its path. A star, a gas cloud, a line of sight geometry that briefly turns the black hole into a lens. The wanderer does not cooperate, it simply moves, and you watch for the moment when its movement intersects with something visible. There are 3 main ways that intersection happens. The first requires a star on the wrong orbit. Every black hole, wandering or otherwise, has a tidal disruption radius, the distance within which the tidal forces from the black hole overcome the self-gravity of an approaching star and pull it apart. A star that wanders within this radius gets stretched, compressed, and eventually shredded into a stream of gas that swings around the black hole and begins to accrete. The accretion releases energy. The energy produces a flare, bright, fast-rising, detectable across optical, ultraviolet, and X-ray wavelengths simultaneously, that can be seen at cosmological distances if the instruments are sensitive enough. This is a tidal disruption event, and for a wandering black hole, the flare appears not at the centre of its host galaxy, but offset from it, displaced by however many kiloparsecs the black hole has drifted. The offset is the signal. A tidal disruption event at the wrong location tells you something massive is there that shouldn't be, by the standard assumption of one central black hole per galaxy. What a tidal disruption event cannot tell you cleanly, on its own, is the mass of the black hole that caused it. The flare's luminosity and timescale give rough estimates, but the uncertainties are wide. This is where X-ray observations become quietly indispensable. X-rays trace emission from the innermost regions of the accretion disk, material moving fastest, closest to the black hole, heated most intensely. The X-ray luminosity and spectral shape carry information about the black hole's mass that optical emission alone does not resolve with the same confidence. For a T2024 TVD, the first off-nuclear tidal disruption event detected optically in 2024, it was Chandra X-ray Observatory follow-up that helped pin down the mass of the wandering black hole with enough precision to distinguish it clearly from the central black hole in the same galaxy. Without the X-ray data, the mass estimate remains soft. With it, the detection firms into something you can actually use. The second detection window requires the black hole to be moving fast enough and through dense enough gas to compress that gas into a detectable shock. A supermassive black hole moving at hundreds or thousands of kilometers per second through the circumgalactic medium, the diffuse gas surrounding the visible galaxy drives a bow shock ahead of it. This is the same physics that creates a sonic boom, scaled up by many orders of magnitude and translated into plasma physics. The compressed gas behind the shock front heats, and hot gas emits. In optical wavelengths, the shock shows up as ionized emission, oxygen, hydrogen stretched along the direction of the motion. In radio, the compressed plasma can produce synchrotron emission. The spatial extent of the feature, combined with its spectral signatures, can identify the wanderer's position and velocity. RBH1, the candidate runaway supermassive black hole confirmed by JWST in 2025 and 2026, was found this way, a linear feature of shocked gas and star formation extending 62 kiloparsecs from its host galaxy. The bow shock at its tip betraying the presence and speed of an object too massive to be anything other than what it appeared to be. The third window is the quietest, an offset AGN, a black hole that is still accreting, still active, but sitting measurably away from the photometric centre of its host galaxy, appears as a displaced point source of AGN emission. Radio surveys particularly can identify these sources with high angular resolution. The VLASS survey identified 328 offset AGN candidates through exactly this method. But confirmation requires ruling out alternative explanations. Dual AGN in an ongoing merger, projection effects, compact background sources. The offset alone is not enough. Spectroscopy, astrometry, and multi-wavelength follow-up are each necessary before the wandering interpretation can be defended with confidence. None of these windows is clean. All three require the universe to provide a specific circumstance, and then require follow-up observations to confirm what the circumstance revealed. Detection is oblique. It always has been. It failed a test, that is, in a quiet way, how it started. Not with a dramatic signal, not with an alarm going off in an observatory somewhere, not with the kind of moment that gets reconstructed in documentary footage later. A transient, a brief brightening in a distant galaxy, was flagged by the Zwicky Transient Facility on August 25, 2024, and when the automated pipeline that processes ZTF detections tried to classify it, the event failed to pass the filter designed to confirm nuclear events. The filter checks whether the transient sits at the centre of its host galaxy. This one did not. The pipeline moved on. The transient did not. ZTF is a wide-field survey camera mounted on the Palomar Observatory's 48-inch Schmidt telescope in California. A system designed to scan the entire accessible northern sky every 2 to 3 nights, looking for things that change. Variable stars, supernovae, asteroids, and tidal disruption events all appear in its data stream as brightness changes against an otherwise static sky. The system processes an enormous volume of data automatically, classifying events into categories and filtering out the ones that don't fit recognized patterns. The nuclear filter exists because tidal disruption events are expected at galactic centers, where supermassive black holes live. An event that fails the nuclear filter is, by the standard assumption, something else. But Faris et al. Conducting spectroscopic follow-up on the flag transient noticed that the spectrum looked like a tidal disruption event. Hydrogen and helium emission lines in the particular ratios characteristic of a star being disrupted, not a supernova, not a variable AGN, not any of the other categories that might produce a similar brightness increase. The spectrum said TDE. The position said otherwise. This inconsistency is the kind of thing that in a less careful analysis might get filed away as a misclassification and forgotten. Instead, the team went back to look more carefully at where exactly the event was occurring. There is something almost mundane about the process of astrometric precision work. Staring at pixel coordinates, comparing source positions against reference catalogues, running centroid measurements, that makes it an unlikely place for a significant discovery to live. But precision is exactly where this discovery lived. Repeated ZTF observations showed a slight but consistent offset between the transient's position and the nucleus of its host galaxy, slight enough to be uncertain in the ground-based data, persistent enough to warrant better eyes. In January 2025, the Hubble Space Telescope turned toward the host galaxy, a massive system roughly 600 million light-years away, in the constellation Hercules, containing a central black hole of approximately 100 million solar masses, and took imaging that resolved the geometry with the clarity only a space-based telescope operating above Earth's atmosphere can provide. The offset was real. The tidal disruption event was occurring approximately 0.8 kiloparsecs, about 2,600 light-years, from the centre of the host galaxy. Not at the edge of the galaxy's outermost regions, not in a satellite system, not anywhere that could be explained by a foreground or background coincidence. Inside the galaxy, clearly associated with it by redshift, but displaced from the nucleus by a distance that the standard picture of where supermassive black holes live simply cannot accommodate. The Chandra X-ray Observatory confirmed what Hubble's imaging had positioned. X-ray emission from the event, tracing the innermost, hottest regions of the accretion disk forming from the disrupted star's debris, was spatially coincident with the optically displaced transient, not with the galaxy's nucleus, with the offset source. The X-ray luminosity and spectral properties were consistent with a black hole of approximately 1 million solar masses. 1 million. Sitting 2,600 light-years from a 100 million solar mass black hole that occupies the actual centre of the same galaxy. 2 black holes in one galaxy. The smaller one off-centre, visible only because a star had the misfortune of crossing its path. The mass ratio tells you something about the likely history. A 1 million solar mass black hole displaced 2,600 light-years from a 100 million solar mass central black hole is not a natural product of in situ formation at that location. The most coherent explanation, and the one the analysis team settled on with appropriate acknowledgement of what remains uncertain, is a minor merger origin. A smaller galaxy, once carrying that 1 million solar mass black hole at its own centre, fell into the larger system, lost its stellar envelope to tidal stripping, and left its naked black hole stranded off-centre, with a dynamical friction timescale too long to return. The star that died revealing it had no way of knowing what it was walking into. A T2024 TVD is, by the technical definition, the first optically selected tidal disruption event confirmed to be occurring off nuclear. Not the first suggested, not the first theorised, not the first modelled, the first caught. The pipeline that flagged it as unusual was right, in the way that good pipelines sometimes are, without knowing why. Every displaced object has a before, not a dramatic before, not necessarily a moment of rupture or collision or obvious violence, just a prior state, a configuration that existed before the one we're looking at now, that explains by its own logic how the current situation came to be. The wandering black hole at the centre of a T2024 TVD, the 1 million solar mass object sitting 2,600 light-years from where a central black hole should be, did not arrive at that position randomly. Randomness doesn't produce specific offsets in specific galaxies with specific mass ratios between the wanderer and the central black hole. What produces that is history. A particular sequence of gravitational events, spread over hundreds of millions of years, that left one object stranded precisely where we find it. The reconstruction begins with a galaxy that no longer exists. Somewhere in the past of the system we now observe, the massive host galaxy, 100 billion solar masses of stars and gas and dark matter, with its 100 million solar mass central black hole, there was a smaller companion, a dwarf galaxy or a low-mass satellite, carrying its own central black hole of roughly 1 million solar masses. This satellite was not a passing interloper. It was gravitationally bound to the larger system, orbiting it, slowly losing energy to dynamical friction with each pass through the host galaxy's outer halo. This is the standard beginning of a minor merger, common, unremarkable in the census of galactic interactions. The satellite's inspiral took time, hundreds of millions of years, probably longer, depending on the initial orbital parameters and the density profile of the host's dark matter halo. With each orbit, tidal forces from the host galaxy reached into the satellite and pulled at its loosely bound outer material. The extended dark matter halo went first, peeling away layer by layer into tidal streams that wrapped around the host galaxy and gradually dispersed. Then the outer stars. Then progressively the inner structure, the satellite's body dissolving. And that word, dissolving, is the one that keeps coming back to me. Because it isn't sudden and it isn't clean. It's a slow becoming part of something else that takes longer than most things humans can imagine, into the larger system's storm stellar halo. The satellite's black hole, initially cushioned by the dense stellar bulge surrounding it, kept its gravitational weight in the medium longer than the stars did. But the stripping was patient, and eventually the cushion thinned. The stellar envelope that had given the black hole its effective gravitational mass in its local environment became threadbare. Then it was gone. What remained was the black hole itself. 1,000,000 solar masses suddenly bare, still moving through the host galaxy's gravitational field, still generating a dynamical friction wake, but now at a mass orders of magnitude lower than the total mass of the satellite it once occupied. Here is where the timescale calculation becomes the most important number in the story. Chandrasekhar's dynamical friction formula contains the mass of the moving object in the numerator of the inspiral timescale. Heavier objects sink faster, lighter objects sink slower. A satellite galaxy of, say, 100 million solar masses sinks through the host on a timescale of perhaps a few billion years. The same satellite's naked black hole, stripped down to 1,000,000 solar masses, experiences a friction timescale roughly 100 times longer. Move the numbers around for the specific density profile of the host galaxy, for the orbital radius of the displacement, for the mass of the black hole, and what comes out for a T2024T, VD's wandering black hole is an inspiral timescale that exceeds the current age of the universe. It cannot return, not in any time frame the universe has remaining at this stage of its history. The black hole is not slowly making its way back to center. It is not on a long elliptical orbit that will eventually bring it home. It is, in the most quietly permanent sense available to orbital mechanics, stuck. This is the part that carries a weight that the numbers alone don't fully convey. The satellite galaxy that brought this black hole here is gone. Its stars have been absorbed into the host's stellar halo, indistinguishable now from the host's own population. The dark matter it carried has dispersed. Every visible trace of the merger has been erased by time. Only the black hole remains, displaced, hollowed of its context, sitting 2,600 light-years from a center it will never reach. The merger that put it there finished its business long ago. The black hole is still carrying the consequence. Nobody was looking for it. That detail matters more than it might seem. Science has a tendency, in the way it gets told afterward, to make discoveries feel inevitable. The right team, the right instrument, the right question, the answer arriving as if pulled toward its finder by some narrative gravity. RBH1 did not work that way. It appeared in an image that was being examined for something else entirely. A linear feature, thin and faint, extending from a compact galaxy in an archival Hubble Space Telescope image, not the target of the observation, not the object anyone had applied for telescope time to study, just a thing that was there in the frame when the frame was opened. Peter van Dokkum, examining the image, noticed it. That is the whole of the discovery moment. A person looking at data and seeing something that didn't belong to the expected content of the field. The galaxy itself, a compact star-forming system at redshift Z equals 0.964, meaning we are seeing it as it existed roughly 7.5 billion years ago, when the universe was less than half its current age, is unremarkable in isolation. Small, blue, actively forming stars, the kind of object that appears in large numbers in deep field imaging, and rarely warrants individual attention. What made this particular galaxy's image frame different was the feature extending from it. A line, not a jet, jets from active galactic nuclei have a particular morphology, a particular spectral signature, a particular behavior at radio wavelengths that was not present here. Not a tidal tail. Tidal tails are diffuse, curved, made of stars and gas following the gravitational geometry of a merger, and this feature was neither diffuse nor curved. It was straight, narrow, extending 62 kiloparsecs from the galaxy's nucleus. That's roughly 200,000 light-years, longer than the entire diameter of the Milky Way, in what looked, in the optical imaging, like a single coherent structure. Straight features of that length don't form easily in the universe. Gravity curves things, tides stretch and distort. The fact that this feature was straight was, in itself, a physical claim. It was saying something about what produced it and how recently. Keck observatory spectroscopy followed the initial imaging, gathering light along the feature's length and splitting it into its component wavelengths. What came back was a spectrum that varied along the feature in a way that carried real physical information. The ratio of ionized oxygen emission to hydrogen emission, the O3 to H beta ratio, a standard diagnostic of what is doing the ionizing, ranged from roughly 1 to 10 along different sections of the feature. At the low end of that range, the ionization pattern is consistent with star formation. Young hot stars doing what young hot stars do, flooding the surrounding gas with ultraviolet photons. At the high end, it points toward fast shocks, gas being compressed and heated by a physical disturbance moving through it at high velocity. Both processes, apparently, were occurring simultaneously along different sections of the same feature. The far end of the feature, the end furthest from the host galaxy, the tip, sat a bright knot of O3 emission with a luminosity of approximately 1.9 times 10 to the 41st power ergs per second, concentrated, spatially compact relative to the broader feature, the kind of emission that, in other contexts, you might associate with a region of intense energy release. This is where the interpretation began to take shape, and I want to be honest that interpretation is the right word, not proof, not certainty, but a coherent reading of what the data was saying. The feature's morphology and spectrum are consistent with the wake of a massive object that recently passed through the circumgalactic medium at high velocity. The shocked gas sections are where the object's passage compressed and heated the surrounding material. The star-forming sections are where the compression pushed gas past the threshold for gravitational collapse, triggering the birth of new stars in material that was not carried by the object but was simply in its path. The bright terminal knot is the bow shock, the place where the object is currently encountering and compressing the circumgalactic medium ahead of it. The object itself is not visible. Whatever is at the tip of RBH1 produces no detectable light of its own. The best fit model, worked through by Van Dockum and collaborators, places the ejection event approximately 39 million years ago. The implied velocity, derived from the feature's length and the estimated time since ejection, comes out at roughly 1,600 kilometers per second. Fast enough to exceed the escape velocity of the host galaxy. Fast enough to carry the object into intergalactic space on a trajectory that will not curve back. Fast enough that whatever is at the tip of RBH1 is, right now, 7.5 billion light-years away from us and still moving. The image that started all of this is still there, in the archive. A faint line in a frame nobody was studying, and the thing at its end is somewhere in the dark, running. Confirmation in science is not a single moment. It is a process, a gradual accumulation of independent measurements, each one adding weight to an interpretation until the interpretation becomes something you no longer need to qualify every time you state it. The 2023 Van Dockum paper presented RBH1 as a candidate. The word candidate was not false modesty, it was epistemically accurate. The evidence was suggestive, the interpretation coherent, the alternative explanations less compelling but not yet ruled out. A straight linear feature with shock and star formation signatures extending 62 kiloparsecs from a compact galaxy, it looked like a runaway black hole's wake. But looking like something and being confirmed as something are separated by whatever measurements close the remaining gap. The gap closed between 2025 and 2026. The instrument that closed it collects near-infrared light and disperses it into spectra with a spatial resolution that ground-based telescopes cannot match from beneath the Earth's atmosphere. JWST's NIR spec, a near-infrared spectrograph operating aboard the James Webb Space Telescope, can take a region of sky and simultaneously collect spectra at thousands of spatial positions within it, building a three-dimensional data cube where every pixel has a full spectrum attached to it. Applied to the tip of RBH1 to the bright 03 knot where the feature terminates, this instrument produced something the 2023 Keck data could only approximate: a velocity map. A spatial picture of how fast the gas at different positions within the bow shock region is moving and in which direction. The geometry matters before the numbers do. A bow shock forms when a supersonic object moves through a medium. The object compresses the gas ahead of it faster than pressure waves can propagate through that gas. Faster, in other words, than the speed of sound in the medium. The compressed gas piles up in a curved front ahead of the object, the shape of the front determined by the ratio of the object's velocity to the sound speed, which is called the Mach number. High Mach number produces a narrow, tight bow shock, the compressed region close to the object's path. Lower Mach number produces a wider, more open shock front. The spatial shape of the emission at the tip of RBH1 was already suggesting something moving at high Mach number. The feature was narrow, the terminal not compact. But the shape alone is ambiguous. The velocity structure is not. NIR spec IFU. Observations of the bow shock region at RBH1's tip of it revealed something specific in the gas velocity field. The gas at different positions within the shock was moving at measurably different velocities. The gas on the side of the shock facing toward us moving at a slightly different line of sight velocity than the gas on the far side. The whole structure tilted fractionally toward the observer, in a way that turned an otherwise symmetric geometry into one where the velocity gradient across the shock front became measurable. This tilt, a coincidence of viewing geometry that Van Dokkum's team acknowledged openly as lucky, is what allowed the shock velocity to be extracted from the spectral data. The O3 emission lines at the bow shock showed velocity offsets across the shock front consistent with gas being accelerated by a supersonic perturber. The numbers, worked through the standard shock physics, produced a velocity for the perturber that was consistent with the earlier estimate from the feature's length and timescale. Something massive, moving supersonically, compressing the circumgalactic medium into a detectable shock front. The confirmation is not that we know exactly what RBH1 is. X-ray observations, the paper notes, were not yet available at the time of the JWST analysis. And without X-ray constraints on the mass of whatever sits at the tip, the mass estimate remains indirect, inferred from the shock's energetics and the feature's overall properties rather than from direct accretion signatures. A supermassive black hole remains the most coherent explanation. A stellar cluster moving at that velocity through that medium cannot produce a shock front of that luminosity. A jet from the host galaxy's nucleus does not produce a linear wake with star formation. The alternatives have been tested and found wanting. But wanting and impossible are different, and careful scientists keep that distance. What the JWST data did, clearly and without ambiguity, is confirm that a supersonic massive object is at the tip of RBH1, not a candidate massive object, not a possible massive object, a confirmed one, measured through the velocity structure of its own bow shock in a dataset that cannot be explained by the known alternatives. The 2023 candidate became the 2026 confirmation, and the object at the centre of that confirmation is still out there, still moving, still compressing gas it will never circle back to. The black hole doesn't make the stars. That distinction matters, and it's easy to lose in the telling. When you describe a 200,000 light-year ribbon of newly formed stars trailing behind a runaway supermassive black hole, the image that forms is of something generative, a creator passing through the dark and leaving life behind it, which is almost poetic and also almost exactly wrong. The black hole carries nothing. It brings no material with it. The stars forming in its wake are not made from anything the black hole contributed. They are made from gas that was already there, already sitting in the circumgalactic medium, already cold enough and dense enough to be on the edge of collapsing under its own gravity, and the black hole moving through that gas at 1,600 kilometers per second simply provided the push that tipped the balance. The push is the thing, not creation, compression. When a massive object moves supersonically through a gaseous medium, and the circumgalactic medium, thin as it is by interstellar standards, is still a medium, still has density, still has pressure gradients that respond to disturbance, it compresses the gas it passes through. Ahead of it, the bow shock does the most dramatic compressing heating gas to temperatures that produce the ionized emission we observe. But along the sides, in the region that trails behind the object, the compression is gentler. Not a shock front more like, and I almost reach for a comparison here before pulling back, because none of them quite hold. More like the wake of a boat pressing outward into the surrounding water. A pressure wave that moves through the medium and briefly increases its local density. In gas that is already near the threshold for gravitational collapse, a brief density increase is enough. Molecular clouds in the circumgalactic medium, already cold enough that thermal pressure is only barely winning against self-gravity, get compressed by the black hole's passage into configurations where self-gravity wins. The cloud collapses. Stars form. Not quickly. Star formation is not an instantaneous process, and the timescale from compression trigger to first stellar light involves hundreds of thousands to millions of years of gradual collapse, fragmentation, and ignition. But the trigger was the black hole moving through. There is a hum to this idea, if you sit with it. Not a literal sound, but the kind of conceptual resonance you get from a mechanism that is both simple and strange simultaneously. A black hole, which is defined by its capacity to consume, passing through gas and causing it to do the opposite. To coalesce. To build. The spectroscopy along RBH1's feature shows both processes happening simultaneously in different sections. Close to the bow shock tip, the O3 to H beta ratio is high, the ionization pattern of fast shocks heating gas by kinetic energy transfer. Further back along the feature, the ratio drops into the range consistent with photoionization by young hot stars. The same object produced both signatures in the same trail, just at different distances behind it, because the shock heating was recent at the tip and the star formation trigger happened further back where the black hole passed earlier. The stars near the far end of the feature are, in a sense, older than the stars near the tip. The wake has a time gradient written into its light. What stays with me, Sadis, and I find myself returning to this detail more than the velocity numbers or the mass estimates, is that those stars will persist long after every trace of RBH1's passage has faded. The bow shock emission will cool, the compressed gas not yet collapsed will slowly re-expand, the black hole itself, if it continues into intergalactic space without encountering further gas, will become invisible again, undetectable, another wanderer in the dark. But the stars it triggered will keep burning. A ribbon of stellar light, 200,000 light-years long, marking the path of something that is already gone by the time the stars are old enough to shine steadily. The black hole doesn't make the stars. It just passes through and they remember. Radio astronomy has a particular quality to it that optical astronomy doesn't quite share. Radio waves pass through dust. They penetrate the obscuring material that hides optical sources. They travel through the interstellar medium largely undisturbed by the gas and grains that scatter visible light. And they carry information about physical processes, relativistic jets, synchrotron emission, from accelerated electrons, the radio continuum of active nuclei, that optical wavelengths cannot access. A radio map of the sky is not a picture of the same sky you see with your eyes or with an optical telescope. It is a map of a different set of phenomena, some of which have no optical counterpart at all, and some of which reveal the presence of things that would otherwise be entirely invisible. The Very Large Array Sky Survey, VLASS, spent 9 years building the most detailed radio map of the sky ever produced, not by staring at individual targets, but by systematically sweeping the entire accessible sky in repeated epochs, each sweep adding to the accumulated picture, the angular resolution of the final product roughly 18 times finer than its predecessor surveys. When the survey completed its final observations in early 2026, what existed was a radio atlas of the sky at 3 GHz, with arcsecond scale angular resolution covering the full northern sky and a substantial portion of the southern. The data in raw form is not immediately a list of wandering black holes. It's a list of radio sources, compact, extended, variable, steady, bright, faint, requiring interpretation and cross-referencing with observations at other wavelengths before any individual source can be assigned a physical identity. The cross-referencing with the Sloan Digital Sky Survey is where the 328 number comes from. SDSS provides optical imaging and spectroscopy of galaxies across a large fraction of the sky, including precise measurements of each galaxy's photometric center, the position of peak optical brightness, which for most galaxies closely tracks the position of the central supermassive black hole. When VLASS radio sources are cross-matched against DSS galaxies, the majority of radio-loud AGN detections sit at the optical center of their host galaxy, as expected. But a subset, 328, in the most recent cross-correlation analysis, sit measurably offset from the optical center. Radio emission at a position that does not coincide with the galaxy's photometric nucleus. This is the signal. Not dramatic in the individual case. An offset of a fraction of an arcsecond in some sources, a few arcseconds in others, but statistically significant across the population, and physically meaningful if the interpretation holds. The interpretation, carefully stated, is that these 328 sources are candidate wandering supermassive black holes, active black holes accreting, producing radio emission that are not sitting where a central black hole should be. The offset between the radio source and the optical nucleus is potentially a direct measurement of how far the black hole has drifted from the center of its host galaxy. Potentially, that qualification is doing real work. Radio offset alone is not confirmation. There are alternative explanations that must be systematically excluded before any individual source in the 328 can be called a confirmed wanderer. The most common alternative is a dual AGN, 2 black holes in an ongoing merger, both active, the radio source associated with one, and the optical nucleus dominated by the other. In a late-stage merger, this can produce an apparent offset that has nothing to do with a kicked or stripped black hole, and everything to do with 2 galaxies that haven't finished combining. Another alternative is projection, a background radio source coincidentally aligned with a foreground galaxy, the spatial coincidence producing a spurious offset when the two are in fact unrelated objects at different distances. Ruling these out requires more than radio data. Spectroscopy at the position of the radio source can determine its redshift. If it matches the host galaxy's redshift, the source is genuinely associated with that galaxy, not a background interloper. High-resolution optical or infrared imaging can search for signs of an ongoing merger, for a second nucleus, for tidal features that would indicate 2 galaxies rather than one displaced black hole. X-ray observations, as established in the detection chapter, can constrain the mass of the accreting object at the offset position. Each of these follow-up steps takes telescope time, real competed-for finite telescope time that is not available for all 328 candidates simultaneously. What VLASS provided is a list, a substantial methodically assembled radio-selected list of places worth looking more carefully. The confirmation work, source by source, wavelength by wavelength, is ongoing. Some of the 328 will not survive scrutiny, others will. The ones that do will be the clearest radio-selected evidence yet that the wandering SMBH population is not a theoretical construct. It is sitting in the data, waiting to be confirmed. Absence is not neutral. When a supermassive black hole is displaced from the centre of its host galaxy, by a merger kick, by tidal stripping, by the incomplete inspiral that leaves a naked black hole orbiting at kiloparsec distances, the galaxy does not simply continue as if nothing changed. The black hole was doing things from that central position, not always dramatically, not always in ways that produced visible AGN emission or obvious jets, but structurally, quietly. The presence of a massive object at the gravitational minimum of a galaxy influences how gas flows, how star formation is regulated, how the galaxy's inner regions evolve over billions of years. Remove it from that position, or rather, relocate it to somewhere that is not the centre, and those influences change, not disappear, change. The first consequence is geometric, and it is more important than it might initially sound. A GN feedback, the process by which an accreting supermassive black hole drives energy back into its surrounding environment through radiation pressure, winds, and jets, is directional. When the black hole sits at the galactic centre, feedback drives outflows from the centre outward. Gas in the inner regions gets heated, pressurised, pushed away from the nucleus. This regulates star formation in the inner galaxy. The heated gas cannot cool efficiently enough to collapse into stars, so the star formation rate in the central region is suppressed. This is standard AGN feedback, and it is one of the mechanisms invoked to explain why massive elliptical galaxies stopped forming stars. Their central black holes, growing large enough to drive powerful outflows, heated the gas reservoir and shut the process down. When the black hole is off-centre, the geometry of this feedback changes entirely. An accreting black hole sitting 2 kiloparsecs from the galactic centre drives outflows from that off-centre position. The outflows are not centred on the galaxy's gravitational minimum. They push gas in directions that depend on where the black hole happens to be at a given moment in its orbit, which changes as the orbit evolves, which means the feedback is not just off-centre but rotating, sweeping through different regions of the galaxy as the black hole moves. The suppression of star formation, if it occurs at all, happens in whichever region the outflows currently reach, not in the organised central to outer gradient that central AGN feedback produces. The galaxy gets reshaped from the outskirts inward, in patterns that don't follow the simple radial symmetry that galaxy formation models typically assume. This has observational consequences that are, at the moment, difficult to disentangle from other processes. A galaxy with an unusual star formation distribution, suppressed in some regions, ongoing in others, in a pattern that doesn't match its structural symmetry, could have a wandering black hole as part of its history. Could. The same pattern could also arise from environmental effects, from a particularly asymmetric merger, from gas stripping by a cluster environment. The wandering SMBH signature in star formation distributions is real in simulations. Identifying it cleanly in observations requires ruling out a long list of competing explanations. Then there is the M-sigma relation and what displacement does to it. The correlation between black hole mass and the velocity dispersion of stars in the galactic bilge is one of the tightest scaling relations in astrophysics, tight enough to be used as a mass estimator, tight enough to have generated substantial theoretical effort to explain its origin. The tightness comes from the fact that the black hole and the bulge co-evolved, each regulating the other's growth through feedback and gravitational influence over billions of years, until the system reached a configuration where the black hole mass and the bulge velocity's dispersion track each other with a scatter of only a fraction of a dex. That coevolution assumed the black hole was at the centre the whole time. A black hole that spent several billion years wandering at kiloparsec distances from the nucleus was not in continuous gravitational dialogue with the bulge it's supposed to correlate with. It was not driving feedback into the bulge from the centre. It was not accreting from the central gas reservoir that the bulge's star formation history tracks. When it eventually returns to the centre, if it does, the relationship between its mass and the bulge's velocity dispersion may not sit on the standard relation. It may sit above it or below it, depending on how the wandering phase altered the relative growth rates of both components. The scatter in the m-sigma relation, not the relation itself, but its width, carries information about the merger and displacement histories of the galaxies in the sample. Wandering black holes are one contributor to that width, not the only one, not even necessarily the dominant one, but a real one, sitting in the data as a broadening of a correlation that would otherwise be tighter. The position of a black hole within its galaxy is not just a location. It is a record of everything that happened to the galaxy since the black hole formed. And a black hole that isn't where it should be is a galaxy that has a story it hasn't finished telling. There are stars that keep time better than any clock humans have built. Pulsars, the rapidly rotating neutron stars left behind when massive stars collapse, emit beams of radio waves from their magnetic poles, and as they spin, those beams sweep across space like the beam of a lighthouse rotating in the dark. When the beam crosses Earth, radio telescopes detect a pulse, and for the most rotationally stable pulsars, the millisecond ones that have been spun up by accreting mass from a binary companion, those pulses arrive with a regularity that makes atomic clocks look slightly approximate. Some millisecond pulsars keep time to a precision of better than 1 part in 10 to the 15th, a fractional stability that no human-engineered timekeeping device has matched. This precision is what makes them useful for something far beyond timekeeping. If a gravitational wave passes between Earth and a pulsar, the wave stretches and compresses the space along the path the radio pulse travels. The pulse arrives slightly earlier or later than it would have in the absence of the wave, not by much, nanoseconds to microseconds, but measurably, given sufficient timing precision and sufficient integration time. A single pulsar gives ambiguous information. An early or late arrival might be a gravitational wave, or it might be irregularities in the pulsar's own rotation, or noise in the interstellar medium the pulse travels through. But an array of pulsars, dozens of them, spread across the sky, all monitored simultaneously over years and decades, allows these effects to be separated. A gravitational wave background produces correlated timing deviations across pulsars, following a specific angular pattern described by a function called the Hellings-Downs curve. Instrumental noise and local effects do not produce that correlation. In 2023, the North American Nanohertz Observatory for Gravitational Waves, NANOGrav, announced, alongside several international pulsar timing array collaborations, that they had detected exactly this pattern. A correlated signal across their pulsar array, consistent with the Hellings-Downs curve at nanohertz frequencies, gravitational wave periods of years to decades. This is not the gravitational wave signal that LIGO detects. LIGO operates at frequencies of tens to hundreds of hertz, detecting mergers of stellar mass black holes and neutron stars, events that last seconds to minutes. NANOGrav's signal sits at nanohertz frequencies, 10 orders of magnitude lower. The physical sources operating at these frequencies are not stellar mass objects, they are supermassive ones. Specifically supermassive black hole binaries in the late stages of inspiral, their orbital periods stretching to years, their gravitational wave emission concentrated at the lowest frequencies the universe produces for compact object mergers. What NANOGrav detected is not the signal from a single such binary. It is the accumulated signal from all of them, every supermassive black hole binary merger that has occurred across the observable universe over billions of years of cosmic history, their gravitational waves overlapping and combining into a stochastic background, a gravitational hum that fills the universe the way the cosmic microwave background fills it with thermal radiation. Not one event, not 10. The integrated consequence of a cosmological population of mergers, each one adding its contribution to the background, the total becoming something detectable precisely because so many events contribute. This is where the connection to everything described in the preceding chapters becomes direct. The gravitational wave background exists only if supermassive black hole binaries merge, regularly, across cosmic time, in sufficient numbers. The signal's amplitude and spectral shape depend on how many mergers occurred, at what masses, at what redshifts, and the signal NANOGrav detected is broadly consistent with theoretical predictions for the merger rate implied by the observed rate of galaxy mergers throughout cosmic history, which means the stall is not permanent. Whatever bridges the final parsec, stellar scattering in non-spherical galaxies, dark matter spikes, gas dynamics, triple interactions, is doing so often enough that mergers happen. Enough mergers to produce the background NANOGrav heard. I find something genuinely settling about that, and I am not entirely sure why. There is something about a signal that took billions of years to accumulate and decades of patient pulsar monitoring to detect, carrying information about events that happened across the entire observable universe that feels not comfortable exactly, but resolved. Like a question that was sitting open for a long time, finally receiving an answer that is partial, indirect, probabilistic, and still somehow enough. The binaries merge. We know this now, not from watching any individual merger, but from listening to all of them at once. The background is quiet, but it has been speaking the whole time. The census has already started. Not in the way a formal survey starts, with a defined beginning and a methodology agreed upon in advance. More the way understanding accumulates, instrument by instrument, detection by detection, each new capability opening a different window onto the same hidden population, the picture assembling itself from whatever angle happens to be accessible at any given moment. 3 instruments define the current frontier of that assembly. Each one approaches the wandering SMBH population from a completely different direction. Each one sees something the others cannot. Vera Rubin Observatory's legacy. Survey of Space and Time began operations recently, and what it does, in simple terms, is watch, systematically, repeatedly, across nearly half the sky every clear night in 6 wavelength bands from near ultraviolet to near infrared, building a database of how the optical sky changes over time. Every object in its field gets revisited roughly every 3 to 4 nights. Transients, things that appear, brighten, fade, are identified automatically and fed into classification pipelines. Rubin's sheer survey volume means it will detect tidal disruption events in numbers that previous surveys could not approach. Current estimates place the expected TDE detection rate at hundreds per year across the full survey. Among those hundreds, some fraction will be off-nuclear. Based on what the Zwicky Transient Facility, a smaller, less sensitive predecessor survey, has already demonstrated with AT2024 TVD and TDE2025 ABCR, the off-nuclear TDE rate is low, but not negligible. Rubin's greater depth and sky coverage will push into regimes where ZTF couldn't reach, finding off-nuclear events at larger distances, smaller offsets, lower luminosities. The prediction from Stein et al. Is that Rubin should detect many dozens of offset TDEs per year with resolvable displacements from their host galaxy nuclei. Many dozens per year, building year on year into a statistical sample large enough to actually constrain the wandering SMBH population's eyes' mass distribution and spatial distribution within host galaxies. Right now that sample is 2, AT2024 TVD and TDE2025 ABCR. 2 data points do not make a population. Rubin turns 2 into hundreds. What Rubin cannot do is measure the masses of the black holes it finds, or resolve the nuclear regions of nearby galaxies with sufficient precision to detect subtle astrometric offsets in quiescent systems. For the mass measurement problem in TDECs, X-ray follow-up remains essential. Chandra and future X-ray observatories doing the work that Rubin's optical data cannot. For the resolution problem in galactic nuclei, a different instrument entirely is required. Gravity Plus is an upgraded interferometric system at the Very Large Telescope Interferometer in Chile, operational from 2026 onward. Interferometry combines light from multiple telescopes separated by large distances, achieving an effective angular resolution equivalent to a telescope as large as the separation between them. Gravity Plus achieves near-infrared angular resolutions of the order of tens of microarcseconds, fine enough to resolve the orbital motions of stars within a few thousand astronomical units of the central black hole in our own galaxy, and to detect astrometric offsets in the nuclei of nearby galaxies that are far too small for any single-dish telescope to see. Applied to the wandering SMBH problem, Gravity Plus can look at the centers of nearby galaxies and ask, is the point source of near-infrared emission from the nucleus precisely centered on the photometric center of the galaxy, or is there a measurable offset? Displacement of even a few parsecs in the nearest galaxies falls within Gravity Plus's reach. This is the kind of measurement that can catch a wandering black hole that is still relatively close to center, not yet far enough to produce an off-nuclear TDE detectable by Rubin, but measurably displaced from where it should be. Gravity Plus works on nearby galaxies. Rubin works on distant ones. Between them, they cover different parts of the same population. Then there is LISA, the Laser Interferometer Space Antenna, 3 spacecraft in a triangular formation, each separated from the others by 2.5 million kilometers, flying in a heliocentric orbit scheduled for launch in 2035, will detect gravitational waves in the millihertz frequency band. This is precisely the band where supermassive black hole binary mergers emit most of their gravitational wave power during the final years and months before coalescence. LISA will not detect the background that NANOGrav hears. It will detect individual events, specific mergers, at specific masses, at specific redshifts, with enough signal-to-noise to characterize the masses and spins of the merging black holes. Every LISA detection is a direct measurement of a merger that would produce a recoil kick. Every kick produces a wanderer, or returns one to center, or ejects one permanently. LISA, in this sense, is not just detecting mergers, it is detecting the events that create the population that Rubin and Gravity Plus are trying to census. The 3 instruments are not redundant. They are sequential, in the deepest sense, each one generating the context that makes the other's measurements meaningful. Rubin finds the wanderers. Gravity Plus resolves where they sit. LISA catches the moments that made them. The census is being built from 3 different directions simultaneously, and the picture, when enough of the pieces arrive, will look nothing like the one we started with. Start with where you are. Not abstractly, not the Milky Way as a diagram in a textbook, the familiar barred spiral viewed from above, arms curling outward from the central bulge. Start with the physical fact of being inside it, which is a different thing entirely. You're embedded in the disk of a galaxy, roughly 26,000 light-years from the center, orbiting at about 220 kilometers per second, surrounded by a stellar neighborhood that extends in every direction and is threaded through with gas and dust and dark matter that you cannot see and barely interact with. The galaxy you live in is not the image, it is the medium you exist within. And somewhere in that medium, if the simulations are right, approximately 10 supermassive black holes are drifting, not at the center, not in any obvious location, distributed through the body of the galaxy, through the halo, through the outer disk regions, through the spaces between the visible structures, on long, slow orbits that carry them through a galaxy they arrived in as the nuclei of smaller galaxies absorbed in the Milky Way's past. The Romulus 25 simulation predicts an average of 12.2 wandering supermassive black holes per Milky Way mass halo within the virial radius, with about 5 within the inner 10 kiloparsecs. 10 orbiting. Right now, the nearest one could be closer than it sounds. If 10 wandering black holes are distributed through a roughly spherical volume with a radius of several hundred kiloparsecs, the average spacing between them is substantial. But distributions are not uniform, and the simulations show that wanderers cluster preferentially outside the disk, in the halo, which is a large volume. The closest wanderer to the solar system might be anywhere from a few thousand to several tens of thousands of light years away. That range is wide enough to feel vague, but the lower end of it, a few thousand light years, is within the Milky Way's disk, within the same spiral arm structure that contains our solar system, within the distance that stellar parallax surveys begin to map with useful precision. There is, as far as anyone knows, no wandering supermassive black hole 1,000 light years away. But there is no compelling observational reason to rule it out either. This is the part I find genuinely unsettling in a way that other parts of this topic don't quite reach. Not frightening, a million solar mass black hole at 1,000 light years is gravitationally negligible at that distance. Its tidal effect on the solar system smaller than the moon's, but unsettling in the quiet sense of realizing that something very large might be very close and completely invisible. The reason we haven't found one is not that we haven't looked in the right places. It is that looking requires a signal, and a quiescent wandering black hole produces none. Without accretion, there is no electromagnetic emission. Without emission, there is no direct detection. The techniques that work for distant wanderers, off-nuclear TDEs, bow shocks in the circumgalactic medium, do not straightforwardly apply to something moving through the Milky Way's disk or halo. A TDE would be visible, certainly. A stellar disruption flare from a wandering black hole in the Milky Way would be extremely bright and would not be missed. But TDEs are rare for any individual black hole, occurring perhaps once every 10,000 to 100,000 years. 10 black holes, each producing a TDE on that timescale, means the Milky Way might see one such event every 1,000 to 10,000 years. We have not been watching with the right instruments for anywhere near that long. Gravitational microlensing offers a quieter approach. A massive black hole passing in front of a background star, as seen from Earth, would gravitationally lens that star's light, brightening it in a characteristic way that depends on the lens mass and the geometry of the alignment. The timescale and shape of the lensing event would distinguish a black hole lens from a stellar one. Current microlensing surveys, including those operated by the OGLE collaboration, and more recently by Roman Space Telescope precursor observations, are sensitive to stellar mass lenses. A supermassive black hole lens would produce a microlensing event on a timescale of years to decades, with a characteristic brightness amplification that differs from stellar events. The surveys exist. The sensitivity is improving. What has not yet happened is the event itself, the right alignment, the right duration, the right geometry, at a time when the survey was watching with sufficient cadence to catch it. It may have already happened in data that hasn't been fully analysed. It may happen in the next decade. It may not happen in any human lifetime, but the galaxy is not hiding nothing. It is hiding something, and the something has mass. There is a particular comfort in thinking that some things stay put, not everything. Clouds move, seasons shift, people leave rooms and don't come back. But underneath the surface level change, the comfortable assumption runs that certain things hold position. The mountain on the horizon, the star you navigate by, the gravitational centre of a galaxy that has been spinning in place for 12 billion years. These feel like fixed points. They feel like the things the rest of the world organises itself around, while everything more temporary drifts and changes in relation to them. The supermassive black hole was supposed to be that kind of thing. It isn't. Or rather, it can be temporarily, under the right conditions, for a span of time long enough that temporary and permanent become difficult to distinguish at human scales. But the forces that can move it are real, and they operate constantly, and the universe has been running them for long enough that the population of displaced, wandering, ejected supermassive black holes is not a footnote. It is a constituency. Millions of invisible giants, each one carrying the gravitational weight of a galaxy's worth of stars compressed into a single object, drifting through the bodies of galaxies that have no obvious record of their presence. The texture of the heavy wool blanket in winter comes to mind, for no particular reason. The weight of it. the way it settles over everything and makes the things beneath it feel fixed and still. That's roughly what the assumption of centrality felt like. Settled, heavy, the kind of assumption that doesn't get questioned because questioning it doesn't seem necessary. What 32 chapters of physics have done, if they've done anything, is lift a corner of that blanket. The mechanics are real. Dynamical friction fails in the right conditions and leaves black holes stranded at kiloparsec distances with no way home. Gravitational wave recoil kicks merged remnants sideways at velocities that can exceed the escape speed of their host galaxy entirely. Three-body slingshot interactions fling the lightest of three competing black holes into intergalactic space at speeds no galaxy's gravity will recover. Tidal stripping hollows out the gravitational cushion that keeps a black hole sinking. Fuzzy dark matter might produce orbits that skip and stutter rather than descend. The final parsec stalls the binary, while the galaxy carries both black holes around, locked in an orbit that looks stable and quietly unresolved. If this video brought you something, a new way of thinking about the galaxy you live in, or just a few quiet hours with an idea worth sitting with, the most direct way to keep this kind of work going is through the community that supports it. A like and a subscription genuinely helps this reach more people. And if you want to contribute more directly, the Patreon link is in the description. Every person who shows up there makes the next video more possible than it would otherwise be. None of these mechanisms are exotic. None of them require new physics or speculative frameworks. They follow from the same gravitational laws that govern everything from falling apples to galaxy formation. The displacement of a supermassive black hole from its galactic center is not an anomaly. It is a gravitational system doing what gravitational systems do, responding to forces, conserving momentum, producing outcomes that are deterministic in principle and surprising in practice. The galaxy is not organized around a fixed point. It is organized around a point that has so far stayed close enough to center that the difference is hard to measure. A temporary arrangement that has persisted for billions of years and may persist for billions more. But temporary is still the right word. Somewhere in the dark outside this galaxy, a black hole is drifting. That sentence opened this video and it closes it, because nothing in between has made it less true. What changed is only the size of the word somewhere. It used to feel like an exception, a rare edge case in an otherwise orderly universe. It is not an exception. It is the ordinary behavior of mass, moving through space, following rules that don't make allowances for how settled we thought things were. The anchor was never fixed. It was just moving slowly enough that we mistook its drift for stillness.